Hey there, cosmic explorers! Welcome to Scientific Discovery Hub, your go-to channel for mind-bending stories about our universe. Today, we are diving into one of the most thrilling astronomical events of the decade, the interstellar Comet 3I Atlas, hurtling through our solar system at breakneck speeds, and its dramatic encounter with Mars this October. Buckle up as we unravel the mysteries of this cosmic traveler and explore what it could teach us about our galaxy. Discovered in 2025 by the Atlas Survey, 3I Atlas is the third known interstellar comet to visit our neighborhood. Unlike ordinary comets trapped in solar orbits, this one's on a one-way ticket, zipping through space at 58 kilometers per second with a trajectory that screams interloper. But why does this matter? Well, 3I Atlas isn't just a pretty light show, it's a cosmic time capsule, carrying secrets about distant star systems and planetary formation. And here's the kicker. As it slams toward perihelion, it'll make a rare close pass by Mars on October 3rd, giving orbiters a golden chance to snap data before it vanishes forever. In this video, we'll break down the science behind 3I Atlas's wild journey. How do objects like this escape their home systems? We'll explain hyperbolic orbits and why this comet's path defies gravity's usual rules. You'll learn how solar heating turns its icy core into a glowing coma, and why its CO2-rich composition hints at a bizarre alien origin. Plus, we'll zoom in on the Martian encounter. Could satellites like Perseverance or ExoMars catch a glimpse of this comet's dusty tail? And what might those observations reveal about its age, or even its parent star system? We'll also tackle big questions. Is 3I Atlas older than our solar system? Could its journey span billions of years through the Milky Way? And while we're at it, we'll separate fact from speculation, like that controversial theory suggesting it might not be natural at all. Whether you're a seasoned stargazer or just curious about our place in the cosmos, this video will take you from the frigid edges of space to the cutting-edge tech tracking 3I Atlas's every move. So hit that subscribe button to join our mission and get ready to explore the science of a comet that's rewriting the rules of the universe. The universe is an endless ocean of motion, where stars drift in slow pirouettes and planets spin in silent waltzes. Amid this grand dance, our solar system is but a fleeting rest stop on a cosmic highway, a temporary haven for travelers born in distant corners of the Milky Way. For millennia, humanity gazed at the night sky, assuming that everything we saw belonged to our celestial neighborhood. But in recent decades, a startling truth emerged. The cosmos is teeming with wanderers. These interstellar objects, ejected from other star systems, drift through the void, their paths unshackled by the gravity of any home. Among them is 3I Atlas, a comet that arrived in 2025 like a ghost from another world, hurtling through our solar system at 58 kilometers per second, a speed so fast it defies the gravitational embrace of the sun itself. What makes these visitors so extraordinary? They arrive unannounced, their origins veiled in the darkness of interstellar space. They are time capsules, carrying the fingerprints of alien star systems. Their trajectories, shaped by the gravitational tugs of unseen worlds, whisper secrets about the birth and death of stars, the architecture of distant planetary systems, and the chaotic beauty of the universe. Yet, despite their rarity, they challenge our understanding of cosmic order. Are they rare anomalies, or do they represent a hidden population of nomads that have always been here, waiting to be noticed? As 3I Atlas streaked past Earth in 2025, its icy heart glowing faintly in the light of distant stars, it became a symbol of humanity's expanding gaze. No longer confined to the familiar, we now peer into the vastness, seeking answers in the trails of these interstellar wanderers. To understand interstellar objects, we must first grasp the nature of their journeys. Unlike asteroids and comets from the Kuiper Belt or Oort cloud, which are bound to the sun's gravity, these interstellar travelers follow hyperbolic trajectories, paths that escape the gravitational pull entirely. Imagine a stone thrown into a pond. Ripples spread outward, but the stone remains. Now imagine a stone flung with such force that it never returns. That is the essence of a hyperbolic orbit. 3I Atlas exemplifies this phenomenon. Discovered in July 2025 by the Atlas Survey telescope in Chile, the comet approached the solar system at a velocity of 58 kilometers per second, far exceeding the escape speed required to break free from the sun's influence. Its orbital eccentricity, a measure of how elongated its path is, reached a staggering 6.1441, far higher than the nearly circular orbits of planets or the elliptical paths of typical comets. For comparison, the first interstellar visitor, 1I Oumuamua, had an eccentricity of 1.2, while 2I Borisov's was 3.4. 3I Atlas's trajectory was so hyperbolic that it appeared almost straight line in the vastness of space, a cosmic arrow aimed at the heart of the solar system. This extreme speed is not arbitrary. It is a relic of the comet's birthplace, a testament to the violent forces that expelled it from its native star system. Most interstellar objects originate from the turbulent cradles of planetary formation, where gravitational interactions with giant planets or passing stars fling icy bodies into the void. Once adrift, they travel for millions or even billions of years, their paths dictated by the gravitational tides of the galaxy. When one of these wanderers finally brushes against the edges of our solar system, it becomes a fleeting guest, its presence a brief but profound reminder of the universe's interconnectedness. Each interstellar object is a relic of a different stellar nursery, a fragment of a forgotten past. 3I Atlas, for instance, may have originated from the thick disk of the Milky Way, a region populated by ancient stars, some of which are over 10 billion years old. If so, the comet predates the solar system by at least 3 billion years, making it a witness to the early days of our galaxy. Its composition, studied by telescopes like Hubble and the James Webb Space Telescope, reveals a world rich in carbon dioxide and water ice, with traces of carbon monoxide and carbonyl sulfide. These chemical signatures hint at a birthplace far from its parent star, where temperatures were cold enough for CO2 to freeze, a clue to the conditions under which it formed. But 3I Atlas is more than a chemical sample. Its trajectory, traced backward through the stars, tells a story of cosmic exile. Unlike the previous interstellar visitors, which came from the direction of the solar apex, the direction in which the sun is moving through the galaxy, 3I Atlas hailed from the southern celestial hemisphere, a region where astronomers had not expected to find such objects. This anomaly suggests that interstellar comets may be more diverse in origin than previously assumed, their paths shaped by the gravitational dance of countless stars. The rarity of these visitors raises a tantalizing question. Are we seeing only the tip of the iceberg? Current surveys, limited by the sensitivity of our instruments, may miss smaller or fainter interstellar objects. Future telescopes, such as the Vera C. Rubin Observatory, promise to uncover more of these cosmic nomads, painting a fuller picture of their role in the galactic ecosystem. For now, each discovery is a puzzle piece, a glimpse into the mechanics of planetary systems beyond our own. Yet the study of interstellar objects is not without its mysteries. The detection of cyanide and atomic nickel in 3I Atlas's Coma, for example, mirrors the chemistry of solar system comets, suggesting that the processes shaping planetary formation may be universal. Meanwhile, the absence of certain compounds, like carbon chain molecules, hints at unique environmental conditions in its birthplace. Such findings challenge our assumptions about the uniformity of cosmic recipes, revealing a galaxy where every star system may have its own distinct signature. As 3I Atlas raced toward perihelion, the point in its journey closest to the sun, it became a case study in the delicate balance between gravity and velocity. The comet's hyperbolic trajectory, shaped by its immense speed, ensured that it would not linger long in the solar system. Yet, its passage offered a rare opportunity to study the physics of interstellar travel. The sun's gravity, though dominant in our cosmic backyard, could not hold this visitor. As 3I Atlas approached, the star's pull accelerated the comet to a peak speed of 68 kilometers per second, a velocity that would carry it away from the solar system forever. Observers tracked its path with precision, noting how it skirted the orbits of Mars and Venus, brushing past Jupiter's gravitational influence in March 2026. Each encounter, however brief, added complexity to its journey, altering its course by minuscule fractions. This interplay of forces is what makes 3I Atlas a marvel of celestial mechanics. Its trajectory, a straight-line escape route in the grand scheme of the galaxy, was a testament to the chaos and order that govern the cosmos. And as it faded from view, its story became part of a larger narrative, the eternal migration of matter across the stars. In the next segment, we will delve deeper into the specifics of 3I Atlas's journey, tracing its path through the solar system and unraveling the physics that govern its flight. From the moment it was discovered to its eventual departure, this comet's voyage offers a window into the vast interconnected tapestry of the universe. Note: the above section constitutes the first part of the 3,000-word script. Adhering to the requested structure and tone, the remaining segments will follow a similar pattern, expanding on the comet's trajectory, observational challenges, and broader implications for astrophysics. In the vast, silent expanse of the cosmos, where time stretches into eons and light bends across galaxies, a traveler emerged from the depths of interstellar space. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System at Rio Hurtado, Chile, 3I Atlas, officially designated C2025N1, Atlas, is a comet unlike any other, with a hyperbolic trajectory that defies the sun's gravitational pull. It hurtles through the solar system at a blistering 58 kilometers per second, its icy heart glowing faintly against the void. This is the story of a cosmic wanderer, a relic from a distant stellar nursery, now fleeting in our neighborhood, as the third interstellar object to be confirmed in human history. 3I Atlas carries secrets of the Milky Way's ancient past and the chaotic dance of planets in far-flung star systems. Its arrival invites us to ponder our place in the universe. Are we alone in the cosmic ocean, or are such travelers common messengers from worlds beyond our sight? The comet's discovery marked a pivotal moment in astronomy. Unlike the sun-orbiting planets and asteroids, 3I Atlas does not belong to our celestial family. Instead, it originates from interstellar space, a fact revealed by its extreme velocity and the sharp curve of its hyperbolic path. As it draws closer to the sun, its icy nucleus warms, releasing clouds of gas and dust that shimmer like ghostly breath in the darkness. This is not merely a passing rock or ball of ice. It is a messenger from the depths of time, a fragment of a long-lost star system, now traversing the solar system on a final, irreversible journey. What makes 3I Atlas extraordinary is not just its origin, but its very existence. For billions of years, it has drifted through the void, untouched by the warmth of any star. Now, for a brief moment in cosmic terms, it graces our skies, offering a glimpse into the enigmatic processes that shape the universe. Through telescopes on Earth and in space, scientists are unraveling its mysteries. What is it composed of? How old is it? And what can it teach us about the birth of stars and planets across the galaxy? This narrative is not just about a comet, it is about the interconnectedness of all things, the threads that bind our solar system to the wider cosmos. 3I Atlas is a reminder that we are not isolated islands in the universe, but part of a grand swirling tapestry of matter, energy and time. To understand 3I Atlas's journey, we must first grasp the elegant and violent forces that govern the universe. Orbital mechanics, the invisible script of celestial motion, dictates whether an object remains in a stable orbit or escapes into the infinite dark. Most objects in the solar system, planets, moons, asteroids, follow elliptical paths, looping endlessly around the sun. These orbits are defined by the balance between inertia and gravity, a cosmic waltz that has persisted for billions of years. But 3I Atlas is different. Its trajectory is not an ellipse but a hyperbola, a sharp open curve that signifies escape. Hyperbolic orbits arise when an object possesses a velocity exceeding the solar system's escape velocity, the critical speed required to break free from the sun's gravitational grip. For 3I Atlas, this velocity is 58 kilometers per second, a speed so immense that it dwarfs the velocities of the previous interstellar visitors. The first such object, 1I Oumuamua, entered our system at 26 kilometers per second, while 2I Borisov approached at 32 kilometers per second. 3I Atlas, however, is a true cosmic sprinter, its speed a testament to its ancient and tumultuous history. The eccentricity of an orbit quantifies its deviation from a perfect circle. For 3I Atlas, this value is a staggering 6.141, far beyond the 1.0 threshold that separates bound mice elliptical from unbound mice hyperbolic. Trajectories. Imagine a comet not gently falling toward the sun like a leaf in a breeze, but racing through the solar system like a bullet fired from a distant gun. This trajectory is not random but the product of gravitational interactions in another star system, where planets and comets engage in a chaotic ballet. Such speeds are achieved through gravitational slingshots, interactions, where a massive object, like a giant planet, transfers momentum to a smaller body, flinging it outward at breakneck velocity. In 3I Atlas's case, it is likely that a colossal planet in its home star system hurled it into interstellar space. Over billions of years, it has drifted through the void, its path nudged by distant stars and nebulae, until it finally reached our corner of the galaxy. The sun's gravity, though immense, cannot halt 3I Atlas's flight. As it swings past our star, its velocity increases due to the sun's pull, but this acceleration is temporary. Once it passes perihelion, the point of closest approach, it will begin to decelerate, its kinetic energy converted into potential energy as it climbs out of the solar system's gravitational well. By the time it exits, it will retain enough velocity to vanish into the cold expanse of interstellar space, never to return. This cosmic escape is a rare phenomenon, yet it underscores the dynamic nature of the universe. The Milky Way is teeming with rogue comets and asteroids, flung from their homeworlds by the gravitational tides of stars and planets. 3I Atlas is one of these exiles, a witness to the birth and death of distant suns. Its journey is a reminder that the universe is not static, but a living, breathing entity, forever reshaping itself through the forces of gravity, time, and chance. As 3I Atlas approaches the sun, its icy nucleus begins to awaken. The solar wind, a stream of charged particles from the sun, strikes the comet's surface, sublimating frozen gases into a luminous coma, a cloud of vapor and dust that expands into the vacuum of space. This process, known as cometary outgassing, transforms the comet from a silent wanderer into a glowing specter, its activity painting the void with trails of carbon dioxide, water vapor, and organic molecules. The Hubble Space Telescope and the James Webb Space Telescope have captured these transformations in exquisite detail. Hubble's images reveal a nucleus shrouded in a coma spanning tens of thousands of kilometers, its glow dominated by dust particles reflecting sunlight. Meanwhile, JWST's infrared vision pierces the haze, detecting the comet's chemical signature, an unusually high concentration of carbon dioxide, a stark contrast to the water-dominated outgassing of most solar system comets. This anomaly hints at a formation history unlike anything in our own backyard. 3I Atlas's nucleus, though obscured by its coma, is estimated to be less than a kilometer in diameter. This small size, combined with its rapid outgassing, suggests a fragile, loosely consolidated structure. Observations by the Very Large Telescope have uncovered even more surprises. Emissions of cyanide gas and atomic nickel vapor, substances rarely detected in comets. These findings challenge assumptions about the chemical diversity of interstellar objects and raise questions about the environments in which they form. The comet's rotation adds another layer of complexity. Early studies struggled to pin down its spin period due to the obscuring coma, but recent analyses suggest a cycle of approximately 16 hours. This irregular rotation, likely influenced by the uneven distribution of mass within the nucleus, causes subtle fluctuations in brightness as the comet turns. Such variations offer clues about the nucleus's shape and internal structure, painting a picture of a body sculpted by the violent processes of its distant past. Yet 3I Atlas is not just a passive observer of the cosmos. Its trajectory, though seemingly solitary, intersects with the planets in a dance of celestial proximity. On 3 October 2025, it will pass within 0.19 AU of Mars, close enough for orbiters to capture detailed observations. Later, it will skim past Venus and Jupiter, its path bending ever so slightly under the influence of these giants. These encounters, though fleeting, provide opportunities to study how the solar system interacts with interstellar interlopers, and how such interactions might shape the evolution of both the comet and the planets. Despite its transient presence, 3I Atlas leaves a lasting imprint. Its journey through the solar system is a fleeting moment in cosmic terms, yet it offers a window into the conditions of its birthplace: the high concentration of carbon dioxide, the presence of nickel and cyanide, and the possibility of an age exceeding 7 billion years, all point to a star system vastly different from our own. Was it born in a cold, distant realm beyond the frost lines of its parent star? Did it endure the cataclysmic collapse of a dying star? These questions remain unanswered, but each observation brings us closer to understanding the universal processes that forge worlds. Even as debates swirl around the nature of 3I Atlas, some suggesting it might be an alien artifact, others insisting on its cometary identity, the scientific community remains united in its pursuit of knowledge. The comet's journey is not just a story of physics and chemistry, but a testament to humanity's curiosity, our drive to decode the cosmos, and our recognition that we are but one thread in an infinite tapestry. As 3I Atlas continues its voyage, the sun's influence grows ever stronger. By 29 October 2025, the comet will reach perihelion, its closest approach to the star, at a distance of 1.36 astronomical units. It will bask in solar radiation that will amplify its outgassing, transforming its coma into a dazzling veil of gas and dust. Yet this intimacy is brief. The sun's gravity, though powerful, cannot hold the comet. As 3I Atlas swings outward, it will shed its temporary brilliance, retreating once more into the cold, dark embrace of interstellar space. But what lies beyond the solar system? What secrets does 3I Atlas carry to the furthest reaches of the galaxy? To answer these questions, we must turn our gaze inward, to the very forces that govern the comet's fate. The next chapter of this story delves into the physics of hyperbolic orbits, not merely as mathematical abstractions, but as the cosmic highways that connect the stars. How do these trajectories shape the destiny of interstellar travelers? What can they tell us about the universe's hidden architecture? As we follow 3I Atlas's path, we are reminded that every object in the cosmos, no matter how distant or fleeting, is bound by the same laws of motion and gravity that govern our own existence. In the coming sections, we will explore the mechanics of escape velocity, the elegance of orbital eccentricity, and the profound implications of a comet that refuses to be trapped. We will uncover how 3I Atlas's velocity and trajectory reflect the chaotic dance of planets in distant star systems, and how its journey might one day inspire missions to intercept future interstellar visitors. For now, as 3I Atlas hurtles toward its final departure, let us marvel at the beauty of its passage, a reminder that even in the vastness of space, every encounter is a conversation between worlds, tone, contemplative, scientifically rigorous, and poetic. Structure maintained as introduction, explanation, transition. Key themes: cosmic connectivity, the physics of interstellar travel, the origins of 3I Atlas, and the universality of natural laws. In the vast tapestry of the cosmos, where galaxies spiral in silent harmony and stars birth and die in fiery dances, a lone wanderer traverses the void. 3I Atlas, an interstellar comet, hurtles through the solar system on a trajectory etched by forces beyond our comprehension. Discovered in July 2025 by the Atlas Survey Telescope in Chile, this icy emissary arrives from the depths of interstellar space, carrying secrets of a distant stellar nursery. Its journey is one of isolation and endurance, a testament to the dynamic nature of the Milky Way. Unlike the familiar comets that orbit the Sun in cyclical patterns, 3I Atlas follows a hyperbolic path, destined to escape the solar system's gravitational embrace. with a velocity exceeding 58 kilometers per second, far swifter than the previous interstellar visitors Oumuamua and Borisov. It defies the quiet order of planetary orbits, a fleeting guest from another realm. As it draws closer to the Sun, 3I Atlas undergoes a transformation. Its nucleus, a frozen heart of ice and rock, begins to awaken under the Sun's radiant touch. Sublimation ignites a cascade of activity, releasing clouds of gas and dust that form a luminous coma and delicate tails. This celestial ballet, choreographed by solar energy, reveals the comet's innermost layers, offering glimpses of its origins. Through telescopes like Hubble and the James Webb Space Telescope, JWST, we witness a spectacle of cosmic chemistry, carbon dioxide, water, and organic molecules swirling in a dance as ancient as the stars themselves. Yet, 3I Atlas is more than a transient visitor. It is a bridge between worlds, a relic of a stellar system long vanished, now sharing its story with our own. Its passage is a reminder of the universe's interconnectedness, a whisper from the dark, echoing across eons. At its core, a comet is a primordial time capsule, forged in the frigid outer reaches of a planetary system. 3I Atlas's nucleus, a solid mass of ice, rock, and organic compounds, remains shrouded in mystery, its true dimensions obscured by the coma it generates. Yet observations from Earth and space telescopes have begun to unravel its secrets. The Hubble Space Telescope estimates the nucleus's diameter to lie between 0.32 and 5.6 kilometers, with the most plausible figure under a kilometer. This diminutive size belies its power to transform under the Sun's gaze. As 3I Atlas ventures inward, solar radiation begins to warm its surface, triggering the sublimation of volatile ices. Water, carbon dioxide, and carbon monoxide, locked in crystalline prisons, transition directly from solid to gas, bypassing the liquid phase. This process, known as sublimation, propels particles of dust and gas outward, forming the coma, a diffuse glowing halo that envelops the nucleus. The coma expands rapidly, stretching thousands of kilometers into space. By July 2025, Hubble imagery reveals a coma spanning 26,400 kilometers, twice the diameter of Earth, while JWST detects a carbon dioxide-rich envelope extending over 348,000 kilometers. These measurements underscore the comet's vigor, its activity amplified by the abundance of CO2, a molecule far more prevalent in 3I Atlas's coma than in typical solar system comets. The dynamics of this transformation are governed by the balance of forces acting on the comet. Solar radiation pressure gently nudges the smallest dust grains, creating a tail that streams away from the Sun. Simultaneously, the gas released by sublimation carries larger particles, forming a second, broader tail. The interplay between these forces shapes the comet's silhouette, a shimmering cross between a ghost and a beacon. Spectroscopic analyses further illuminate the chemical complexity of 3I Atlas's coma. JWST's near-infrared instruments detect not only CO2 and water, but also traces of carbon monoxide, carbonyl sulfide, and even atomic nickel, a signature of the comet's internal heat and chemistry. The presence of cyanide gas, identified by the Very Large Telescope, hints at organic processes, linking this interstellar traveler to the building blocks of life. Yet 3I Atlas's behavior is not uniform. Its coma exhibits a reddish hue, a tint shared with D-type asteroids and other comets, likely due to irradiated organic compounds. The dust ejected from its surface varies in size and speed. Tiny grains flee at 22 meters per second, while larger particles drift more slowly, carried by the comet's own momentum. These differences create a layered structure within the coma, a stratified cloud that evolves as the comet nears perihelion. By October 2025, when 3I Atlas reaches its closest approach to the Sun at 1.36 AU, the coma will expand further, its density peaking as the nucleus sheds layers of ice and rock. This crescendo of activity will culminate in a tail that stretches millions of kilometers, a luminous arrow pointing away from the Sun, a testament to the comet's transient brilliance. The composition of 3I Atlas's coma is a Rosetta Stone for deciphering its origins. Unlike solar system comets, which typically exhibit a water-dominant chemistry, 3I Atlas is unusually rich in carbon dioxide. JWST's August 2025 observations reveal a CO2 to water ratio of 8:1, a stark departure from the 1:1 to 2:1 ratios observed in Halley's Comet or Borisov. This anomaly suggests that 3I Atlas formed in an environment where CO2 was abundant, likely beyond the CO2 frost line, the region in a protoplanetary disk where temperatures are low enough for CO2 to condense into ice. Such a location would place it farther from its parent star than the equivalent water frost line, implying a formation history distinct from most solar system comets. But why has water ice not sublimated more prominently? One hypothesis posits a protective crust, a layer of refractory material that insulates the nucleus and delays the release of water. Alternatively, the comet's chemistry may reflect a unique evolutionary path, perhaps influenced by the intense radiation of its host star or interactions with nearby nebulae. The presence of heavy CO2 isotopes, carbon-13, further complicates the picture, hinting at a history of processing in a high radiation environment. These clues align with the idea that 3I Atlas hails from a stellar system unlike our own, one where CO2 played a dominant role in shaping the building blocks of planets. The comet's age adds another layer of intrigue. If 3I Atlas originates from the Milky Way's thick disk, a population of ancient stars with low metallicity, it could be up to 14 billion years old, predating the solar system by nearly 3 billion years. This would make it the oldest interstellar object ever observed, a relic from an era when the galaxy was young and chaotic. Its trajectory, tilted 5 from the ecliptic and retrograde in direction, suggests it was flung from its home system by gravitational interactions with massive planets or passing stars. Such a violent expulsion mirrors the fate of many comets in the Oort cloud. Yet 3I Atlas's speed and hyperbolic excess velocity confirm its extraterrestrial provenance. Perhaps most striking is the comet's potential to reshape our understanding of interstellar chemistry. The detection of nickel and cyanide in its coma challenges assumptions about the distribution of metals in cometary bodies. While nickel vapor is common in solar system comets, the absence of iron, a typical companion to nickel, raises questions about the comet's internal composition. Was 3I Atlas's parent star metal poor? Did its formation environment favor the preservation of certain elements over others? These mysteries underscore the value of 3I Atlas as a cosmic messenger, offering a window into the diversity of planetary systems across the galaxy. As 3I Atlas continues its solar pilgrimage, its path brings it perilously close to Mars. On 3 October 2025, the comet will pass within 0.19 AU, 28 million kilometers, of the red planet, a distance that, while safe, presents an opportunity for unprecedented observation. Mars orbiters like NASA's Perseverance and ESA's ExoMars Trace Gas Orbiter may capture views of the comet's coma and tail, analyzing its composition from a vantage point unattainable by Earth-based telescopes. This encounter could reveal how 3I Atlas interacts with the Martian atmosphere, should any particles reach the planet's vicinity. More importantly, it will test the limits of our observational capabilities, pushing the boundaries of what we can learn from an interstellar visitor. This fleeting rendezvous with Mars marks a pivotal moment in 3I Atlas's journey, a final act before it departs the solar system forever. As the comet's activity peaks in October, its coma will expand to its maximum size, casting a ghostly glow against the Martian sky. From this vantage, we may glimpse the full breadth of its transformation, a farewell performance orchestrated by the sun. Yet the data gathered during this encounter will endure, a legacy of discovery that bridges the gap between Earth and the stars. In the chapters ahead, we will delve deeper into the significance of this Martian encounter, exploring how it reshapes our quest to understand the origins of comets and ourselves. In the vast expanse of the cosmos, where the laws of physics govern the dance of stars and the silent migration of planets, a visitor from the depths of interstellar space has entered our solar system. 3I Atlas, an enigmatic comet, bearing the prefix of the third confirmed interstellar object to traverse our cosmic neighborhood, now glides through the solar system with a speed and trajectory unlike any natural-born wanderer of the sun. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS, in Chile, this comet is not bound by the gravitational pull of our star. It is a traveler from a distant stellar cradle, a relic of another world's youth. Its arrival marks a moment of profound significance, a reminder that the universe is not a solitary expanse but a tapestry of interconnected systems, each thread weaving the story of existence itself. 3I Atlas carries with it the secrets of its birthplace, a region of the Milky Way shrouded in mystery. Its hyperbolic trajectory, defined by an orbital eccentricity of 6.141, ensures that it will never return to the solar system. The comet's speed, a blistering 58 kilometers per second relative to the Sun, defies the slowness of planetary orbits, a testament to the forces that hurled it into the void. Unlike the comets that originate from the Kuiper Belt or the distant Oort cloud, 3I Atlas does not belong to the solar family. Instead, it is an interloper, a messenger from the interstellar abyss, offering a rare opportunity to study the chemistry and dynamics of worlds beyond our own. As it journeys inward, the Sun's radiant energy begins to awaken the comet from its deep space hibernation. The icy nucleus of 3I Atlas, though obscured by a veil of gas and dust, begins to sublimate, releasing carbon dioxide, water vapor, and other volatile compounds into the vacuum. This outgassing forms a luminous coma, a glowing halo that stretches across the darkness, and a delicate tail that points away from the Sun. Observatories across the globe, from the Hubble Space Telescope to ground-based instruments like the Very Large Telescope, have turned their gaze toward this celestial intruder, eager to decipher its origins and unravel the clues it leaves in its wake. The discovery of 3I Atlas is not merely an astronomical milestone. It is a philosophical reckoning. It reminds us that we are not alone in the universe, not in the sense of intelligent life, but in the sense of shared cosmic heritage. Every star, every planet, every comet is a fragment of the same grand design, shaped by the same fundamental forces. And yet 3I Atlas is a reminder of the vast distances that separate us from our neighbors. It has traveled billions of years to reach us, a time so immense that it dwarfs the history of humankind. Its arrival is a whisper from the past, a voice from a place we have yet to explore, urging us to look outward, to seek understanding in the infinite expanse beyond our home. The first glimpse of 3I Atlas came as a faint smudge in the night sky, a ghostly apparition lost among the stars. On 1 July 2025, the Atlas Survey Telescope at Rio Hurtado, Chile, captured its image, marking the beginning of a scientific odyssey. At that moment, the comet was 4.5 AU from the Sun, a distance greater than the orbit of Jupiter, yet its hyperbolic trajectory hinted at a journey far beyond the confines of the solar system. Initial observations revealed a peculiar object, neither asteroid nor comet in the conventional sense, but something in between. Its motion was too swift for a native solar system body, and its faint glow suggested the presence of a coma, the telltale sign of cometary activity. The discovery was submitted to the International Astronomical Union's Minor Planet Center, where astronomers scrambled to confirm its nature and trajectory. As follow-up observations poured in from telescopes around the world, the true character of 3I Atlas began to emerge. The Zwicky Transient Facility in California and the Canada-France-Hawaii Telescope in Hawaii contributed data that refined its orbit, revealing an eccentricity of 6.141, the highest recorded for any interstellar object. This value placed 3I Atlas on a path that would never allow it to return, a one-way ticket to the interstellar void. The comet's velocity, 58 kilometers per second relative to the Sun, was another anomaly. It moved faster than the previous interstellar visitors, 1I Oumuamua and 2I Borisov, which had velocities of 26 and 32 kilometers per second respectively. This speed, known as the hyperbolic excess velocity, confirmed what astronomers had long suspected. 3I Atlas was not born in the solar system. It was a traveler from another star's realm, yet the comet's identity remained elusive. Was it a frozen asteroid, a rogue planet, or a true comet in the traditional sense? Early observations were inconclusive. Some astronomers, like Alan Hale, reported no cometary features, while others noted a faint coma and a subtle elongation in its appearance, suggesting the presence of a dust tail. By late July, the debate was settled when the Deep Random Survey in Chile, the Lowell Discovery Telescope in Arizona, and the Canada-France-Hawaii Telescope confirmed the existence of a coma. The comet was active, its nucleus releasing gas and dust into space. The designation 3I was soon assigned, cementing its status as the third interstellar object ever discovered. What made 3I Atlas particularly intriguing was its origin. Tracing its trajectory backward through time, astronomers found that it had approached the solar system from the direction of the constellation Sagittarius, near the heart of the Milky Way. This region is dense with stars and interstellar matter, a chaotic environment where gravitational interactions could have dislodged the comet from its parent system. The comet's high velocity and vertical motion, relative to the galactic plane, suggested it belonged to either the thin or thick disk population of the Milky Way. If the latter, 3I Atlas could be at least 7 billion years old, older than the solar system itself. Such an age would make it a relic of the galaxy's earliest days, a cosmic fossil from an era when stars were young and planets were forming. As the months passed, the comet's activity intensified. Observations by the Hubble Space Telescope and the James Webb Space Telescope revealed a coma rich in carbon dioxide and water vapor, with traces of carbon monoxide and carbonyl sulfide. The Very Large Telescope detected cyanide gas and atomic nickel vapor, elements commonly found in comets, but rarely observed in such quantities. These findings painted a picture of a comet with a unique composition, one that differed significantly from the icy bodies native to the solar system. The implications were profound. 3I-80 was not just a visitor, it was a messenger carrying the chemical signature of a distant star system. Despite its scientific promise, 3I Atlas posed no threat to Earth. Its closest approach would take place at a distance of 1.8 AU, placing it safely beyond the orbits of Venus and Mars. Yet the comet's proximity to these planets offered opportunities for observation. Mars, in particular, would serve as a vantage point, as the comet passed within 0.19 AU of the Red Planet in October 2025. Orbital spacecraft like NASA's Perseverance rover and the European Space Agency's ExoMars Trace Gas Orbiter would attempt to capture images and spectra, providing insights into the comet's structure and evolution. For the first time, humanity would have a direct view of an interstellar object from a planetary platform, a perspective unattainable from Earth. The discovery of 3I Atlas was not merely an academic triumph. It was a testament to the power of global collaboration. Over 120 observations from 31 different observatories contributed to the comet's characterization, a collective effort spanning continents and cultures. From amateur astronomers scanning the skies with backyard telescopes to professional teams operating the most advanced instruments on Earth and in space, the study of 3I Atlas united scientists in a shared pursuit of knowledge. It reminded us that the universe is not a solitary frontier, but a shared domain, one that demands cooperation and curiosity to fully understand. As 3I Atlas continued its journey, the questions surrounding it multiplied. What was its parent star? How had it escaped its native system? What secrets lay within its icy nucleus? The answers, like the comet itself, were waiting to be uncovered, each revelation bringing us closer to the truth of our place in the cosmos. As 3I Atlas hurtles through the solar system, its trajectory tells a story written in the language of gravity and motion. The comet's path, a perfect hyperbola, is a testament to its interstellar origins. Unlike the elliptical orbits of planets and native comets, which loop endlessly around the Sun, 3I Atlas's route is a single sweeping arc, a one-time encounter with our star before it vanishes back into the interstellar dark. This trajectory is not arbitrary. It is the product of gravitational forces, the unseen hands that guide the dance of celestial bodies across the void. The Sun, the dominant mass in the solar system, attempts to bend the comet's path with its gravity. But 3I Atlas is moving too fast to be captured. Its hyperbolic excess velocity of 58 kilometers per second is a speed that no native object could achieve without an external force. The only plausible explanation is that the comet was ejected from another star system, flung into the interstellar void by the gravitational slingshot of a massive planet, or the chaotic tug of a passing star. This ejection event, however, occurred billions of years ago, long before the solar system itself took shape. The comet's journey through the Milky Way has been a lonely one, a voyage across the chasm of time and space. Tracing the comet's trajectory backward in time reveals a path that originates from the southern celestial hemisphere in the direction of the constellation Sagittarius. This region, near the galactic center, is a dense and dynamic area, teeming with stars and interstellar clouds. Here, the gravitational interactions between stars are frequent, and the likelihood of planetary disruptions is high. It is in this chaotic environment that 3I Atlas likely formed, a frozen remnant of a protoplanetary disk that once swirled around a distant star. The comet's current velocity and orientation suggest that it belongs to either the thin or thick disk population of the Milky Way. The thin disk, which includes the majority of the galaxy's younger stars, is relatively flat and orderly, while the thick disk is older, more diffuse and populated by stars with lower metallicities, those with fewer heavy elements than the Sun. If 3I Atlas is a member of the thick disk, its age could be staggering. AMPA's study by Matthew Hopkins and collaborators in July 2025 estimated that the comet is between 7.6 and 14 billion years old, making it older than the solar system itself. This would place its formation in an era when the Milky Way was still young, when the first generations of stars were forming and the galactic disk was taking shape. The comet's composition supports this theory. Its high abundance of carbon dioxide and low levels of certain organic compounds suggest that it formed in a different stellar environment than the comets of the solar system. These differences offer a rare glimpse into the diversity of planetary systems beyond our own, a window into the conditions that shaped worlds in distant corners of the galaxy. Yet the comet's journey is not a static path. Over the billions of years it has spent wandering the interstellar void, 3I Atlas has likely encountered other stars and interstellar clouds, each encounter subtly altering its trajectory. The study by Yang Guo and collaborators in September 2025 revealed that the comet may have passed within 1 parsec 3.3 light-years of 25 known stars in the past 10 million years. These close encounters, though not sufficient to alter its overall course, may have influenced its velocity and orientation. The comet's vertical motion relative to the galactic plane, its movement above and below the disk, is particularly significant. AMPA's velocity component of plus 18.5 kilometers per second in the Watts direction suggests that 3I Atlas is not confined to the galactic plane, but is instead moving on an inclined path. This tilt implies that the comet has spent much of its existence outside the main disk of the Milky Way, traversing the galactic halo, a region dominated by older stars and dark matter. The implications of 3I Atlas's age and origin are profound. If the comet is indeed older than the solar system, it predates the formation of the planets, the asteroid belt, and even the Sun itself. Such an object would be a relic of the earliest days of the galaxy, a time when stars were forming at an accelerated pace and the Milky Way was still assembling its structure. The fact that 3I Atlas has survived this immense journey without being destroyed or captured by a star speaks to the resilience of cometary bodies. It is a survivor, a wanderer that has endured the chaos of interstellar space for eons, carrying with it the chemical signature of its birthplace. As 3I Atlas approaches perihelion on 29 October 2025, the Sun's gravity will accelerate it to its fastest speed, 68 kilometers per second, before it begins its inevitable retreat into the void. The comet's closest approach to the Sun, at 1.36 AU, places it between the orbits of Earth and Mars, yet it will not come near either planet. Instead, it will pass by Venus and Jupiter, using their gravitational fields to refine its trajectory. The encounter with Jupiter in particular will be a defining moment. Though the comet will not be captured by the gas giant, its passage will provide an opportunity to study its composition in greater detail. Instruments aboard the Juno spacecraft currently orbiting Jupiter, may be able to detect subtle changes in the comet's motion or composition as it passes by. The journey of 3I Atlas is a cosmic clockwork, a precise interplay of forces that have guided its path across the galaxy. Each gravitational interaction, each collision with interstellar matter, has left its mark on the comet's trajectory, shaping the arc of its journey. Yet, despite these influences, the comet remains on its one-way path, a traveler destined to vanish beyond the reach of the solar system. As it continues its voyage, 3I Atlas serves as a reminder of the vastness of the universe and the intricate web of connections that bind its inhabitants. It is a message in a bottle from the past, a fragment of another star's history drifting through the void, waiting to be discovered. In the vast, silent expanse of the cosmos, where galaxies spiral like ancient dancers and stars flicker like distant memories, a single object emerged as a harbinger of mystery. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas, in the arid skies of Rio Hurtado, Chile. 3I Atlas, also known as C2025N1, Atlas, was not merely another comet. It was a traveler from beyond the solar system, a cosmic wanderer hurtling through the heavens at a blistering 58 kilometers per second. Its arrival marked the third confirmed interstellar visitor to our celestial neighborhood, joining the enigmatic 1I Oumuamua and 2I Borisov as silent messengers from the far reaches of the Milky Way. Yet 3I Atlas was different. Its trajectory, its composition, its age, all hinted at a story older than the solar system itself, a tale etched into the fabric of the universe. As telescopes turned their gaze toward this strange visitor, the scientific community and stargazers alike were drawn into a profound contemplation. What secrets does 3I Atlas carry? Where did it originate? And what does its passage through the solar system tell us about the origins of life, the evolution of stars, and the boundless expanse of time? This script invites you to journey alongside 3I Atlas, from the moment of its discovery to the unraveling of its cosmic origins, and to ponder the existential questions it raises about our place in the cosmos. When the Atlas survey first spotted 3I Atlas, it was already deep within the inner solar system, a ghostly apparition at 4.5 astronomical units, AU, from the Sun. Its path, however, betrayed no allegiance to our star. With a hyperbolic excess velocity of 58 kilometers per second, far exceeding the escape velocity of the Sun, it was clear that 3I Atlas was not bound by the gravitational embrace of our celestial home. The comet's trajectory, defined by an orbital eccentricity of 6.14, was so extreme that its path appeared almost linear, slicing through the solar system like a comet-shaped spear. Initial confusion reigned as astronomers debated whether 3I Atlas was an asteroid or a comet. Early observations showed no signs of cometary activity, but as the object neared the Sun, the truth emerged. By 2 July 2025, telescopes revealed a diffuse coma, a cloud of gas and dust spewing from its nucleus. As it began to sublimate under the Sun's warming touch, the discovery was confirmed by the International Astronomical Union, and 3I Atlas was officially designated as the third interstellar object. What set 3I Atlas apart from its predecessors, 1I Oumuamua and 2I Borisov, was its rich chemical profile. Observations by the James Webb Space Telescope, JWST, and the Very Large Telescope, VLT, unveiled a coma teeming with carbon dioxide, water ice, carbon monoxide, and traces of cyanide and atomic nickel. These molecules, common in solar system comets, hinted at a shared heritage despite 3I Atlas's alien origin. Yet its abundance of carbon dioxide, 8 times that of water, was unprecedented. Such a ratio suggested a formation far from its parent star, beyond the CO2 frost line, where temperatures are frigid enough for volatile ices to condense. The comet's activity was equally intriguing. As it approached the Sun, its coma expanded, and its dust ejection rates mirrored those of 2I Borisov. Though at a lower intensity, small particles, accelerated by solar radiation pressure, formed a faint tail extending millions of kilometers. Meanwhile, A peculiar sun-facing plume of dust hinted at localized heating on the nucleus, a phenomenon seen in distant comets like CETH 2014 UN 271. These features painted a picture of a dynamic, active world, one that had preserved the primordial chemistry of its birthplace for eons. 3I Atlas's journey through the solar system was as dramatic as it was fleeting. Its perihelion, the closest approach to the Sun, occurred on 29 October 2025 at a distance of 1.36 AU, placing it between the orbits of Earth and Mars. Yet, unlike the comets of our system, 3I Atlas would not linger. Its hyperbolic trajectory ensured its escape, propelling it back into interstellar space at a velocity that would outpace the solar system's gravitational pull. The comet's alignment with the ecliptic plane added another layer of intrigue. Its retrograde inclination of 175 Dork meant it traveled in the opposite direction to most solar system bodies, a stark reminder of its extraterrestrial nature. Despite its proximity to Venus, Mars, and Jupiter, 3I Atlas posed no threat to Earth, its closest approach remaining safely at 1.8 AU. For observers on our planet, however, the comet's visibility was constrained by its solar elongation. From Earth, it would vanish behind the Sun during perihelion, leaving only Martian orbiters to witness its closest moments. The true revelation of 3I Atlas lay in its age. By analyzing its velocity components, radial, transverse volts, and vertical watts, astronomers traced its origin to the Milky Way's thick disk, a population of ancient stars formed in the galaxy's turbulent youth. The thick disk, older and more metal-poor than the thin disk, where our Sun resides, suggested that 3I Atlas could be between 7.6 and 14 billion years old. That placed it well beyond the age of the solar system, 4.6 billion years, making it a relic from an era when the Milky Way was a chaotic crucible of star formation, mergers, and supernovae. This staggering antiquity raised profound questions. Had 3I Atlas witnessed the birth of the first stars? Did it drift through the remnants of long-dead planetary systems? Its journey through interstellar space, spanning billions of years, was a testament to the galaxy's dynamic history. Close encounters with stars and nebulae may have altered its trajectory, but its core remained unchanged, a frozen time capsule carrying the chemistry of a bygone epoch. Studying 3I Atlas offered insights into the formation of comets in diverse stellar environments. Unlike solar system comets which formed in the Kuiper belt or Oort cloud, this interstellar wanderer hailed from a protoplanetary disk around a distant star. Its CO2-rich composition hinted at a formation beyond the CO2 frost line, suggesting that icy bodies could form in a wide range of stellar systems. Moreover, its metal-poor chemistry aligned with the thick disk's low metallicity stars, reinforcing the idea that 3I Atlas's parent star was among the galaxy's earliest inhabitants. The comet's survival over billions of years also challenged assumptions about the longevity of cometary nuclei. While solar system comets lose mass rapidly when heated by the Sun, 3I Atlas's distant perihelion, -1.36 AU, spared it from catastrophic disintegration. Its ability to retain volatile ices despite millennia of travel suggested that interstellar comets might be more resilient or more common than previously thought. Perhaps the greatest value of 3I Atlas lay in its role as a Rosetta Stone for interstellar chemistry. The detection of cyanide and atomic nickel in its coma mirrored findings in 2I Borisov, yet the absence of carbon chain compounds, like C2 and C3, set it apart. This contrast hinted at differences in the chemical environments of its parent star system versus our own. The high CO2 to water ratio, too, defied expectations, raising questions about the processes that govern volatile distribution in protoplanetary disks. For astrobiologists, 3I Atlas was a tantalizing target. Could its carbon-rich chemistry hold clues to the origins of organic molecules in the galaxy? The presence of amorphous water ice and carbonyl sulfide suggested that the building blocks of life might be more widespread than we imagine. In a universe teeming with comets, perhaps the seeds of biochemistry are sown across the stars. Despite its scientific richness, 3I Atlas remains a fleeting guest, Its rapid exit from the solar system leaves little time for direct exploration. Launching a spacecraft to intercept it from Earth is impractical, requiring an energy expenditure beyond current capabilities. Yet, Mars-based missions offer a glimmer of hope. The comet's close approach to the red planet in October 2025 could allow orbiters like NASA's Mars Reconnaissance Orbiter to capture detailed images, probing its nucleus and coma in ways impossible from Earth. Even as 3I Atlas vanishes into the interstellar void, its legacy endures. The data it leaves behind, spectral fingerprints of its chemistry, measurements of its activity, and clues to its origin, will fuel decades of research. Future missions, such as the ESA's Comet Interceptor, may one day intercept another interstellar comet, building on the foundation laid by 3I Atlas. The story of 3I Atlas is not just about a single comet. It is a story of curiosity, of humanity's unyielding drive to understand the cosmos. As we trace its path from the galactic thick disk to the heart of the solar system, we glimpse the interconnectedness of stars, planets, and the icy relics that bind them. In its ancient nucleus lies the memory of a galaxy's infancy, a reminder that we are all travelers in the same vast, unfolding story. In the vast, silent expanse of the cosmos, 3I Atlas drifts, a solitary traveler born of distant stellar fires, discovered on 1 July 2025 by the Atlas Survey Telescope in Chile. This interstellar comet carries secrets etched into the fabric of the Milky Way. Its arrival in our solar system is a fleeting whisper from a galaxy-wide symphony, a reminder that the universe is a dynamic, interconnected web of motion and memory. Unlike the familiar comets of our own system, 3I Atlas does not originate from the Oort cloud or the Kuiper belt. Instead, it hails from the interstellar void, a relic of another star's birthright. To trace its path is to unravel the story of its origin, a journey spanning eons and galaxies. Yet, as with all cosmic travelers, the road it has traveled is not linear. Gravitational tides, stellar encounters, and the passage of time have reshaped its trajectory, leaving behind a trail of enigma. Where did 3I Atlas begin its voyage? And what does its journey reveal about the universe we inhabit? To decode the origins of 3I Atlas, astronomers employ a blend of astrometry, spectroscopy, and dynamical modeling. The comet's hyperbolic trajectory, a path that curves sharply inward before escaping the sun's grasp, speaks volumes. With an orbital eccentricity of 6.141, 3I Atlas moves through our solar system like a ghostly apparition, its speed far exceeding that of native comets. This velocity, 58 kilometers per second relative to the Sun, places it among the fastest interstellar visitors ever recorded. But speed alone is not enough to determine its provenance. By reconstructing its trajectory backward in time, scientists trace its path through the Milky Way's gravitational labyrinth. The comet's current motion reveals critical clues. Its velocity components, radial, transverse, volts, and vertical, loss, suggest it hails from the galactic thick disk, a region populated by ancient stars older than the solar system. The thick disk inhabitants, formed billions of years ago in the Milky Way's turbulent youth, carry signatures of a different era, lower metallicity, higher velocities, and orbits tilted relative to the galactic plane. 3I Atlas's vertical velocity, watts plus 18.5 kilometers per second, aligns with this population, hinting at an origin in the thick disk's shadowed depths. Yet, the thick disk is not a static realm. Over billions of years, the comet's path has likely been perturbed by encounters with stars, molecular clouds, and the Milky Way's own gravitational tides. These interactions scatter interstellar objects like stardust, erasing direct links to their birthplaces. Thus, 3I Atlas's true origin remains veiled, a puzzle pieced together from fragments of its journey. What does 3I Atlas's origin tell us about the universe? If it indeed belongs to the thick disk, its age could surpass 7 billion years, older than the solar system itself. Such an object is a relic from the Milky Way's formative years, a witness to the birth of stars and planets in a primordial cosmos. Its composition, rich in carbon dioxide, and bearing traces of cyanide and nickel, offers a glimpse into the chemistry of a distant stellar nursery. Unlike solar system comets, which formed under the sun's influence, 3I Atlas's volatile rich nucleus suggests it originated far from its parent star, beyond the CO2 frost line. This implies a history of violent ejection, perhaps from a binary star system or a chaotic planetary architecture. Yet, 3I Atlas's southern origin challenges long-held assumptions. Most interstellar objects are expected to arrive from the solar apex, the direction of the sun's motion through the galaxy. Its arrival from the opposite hemisphere forces a re-evaluation of galactic dynamics. Could the Milky Way's thick disk be a more prolific cradle of interstellar wanderers than previously thought? Or does 3I Atlas represent an anomaly, a rare survivor of a forgotten epoch? These questions ripple outward, touching on the distribution of planetary systems, the frequency of stellar mergers, and the role of gravitational scattering in shaping the galaxy. The comet's journey also underscores the fragility of cosmic memory. Over billions of years, its path has been reshaped by stellar encounters, each interaction a brushstroke altering its trajectory. This erasure of origin mirrors humanity's own struggle to understand the universe. Like 3I Atlas, we are explorers seeking to decode a past obscured by time and distance. Yet, in its chemical fingerprint and orbital signature, the comet offers a bridge between epochs, a testament to the enduring legacy of stellar evolution. If 3I Atlas is a singular visitor, it is not the last. Its discovery hints at a vast, unseen population of interstellar comets and asteroids drifting through the galaxy, each carrying the imprint of a distant star. Future surveys, armed with the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, may unveil thousands more, transforming our understanding of planetary formation and galactic ecology. These objects are not mere curiosities, they are cosmic messengers, ferrying the building blocks of life across the void. But what of the possibility that 3I Atlas is not entirely natural? Amper's controversial hypothesis posits that its trajectory and composition could hint at an artificial origin. Though most scientists dismiss this as speculative, yet the debate itself reflects a deeper truth. The universe is stranger than we imagine, whether as a product of stellar chaos or an artifact of an alien civilization. 3I Atlas invites us to ponder the limits of our knowledge. In its passage, it whispers of a cosmos teeming with stories yet to be told. As 3I Atlas continues its silent flight beyond the solar system, it leaves behind a trail of questions. What other interstellar travelers await discovery? How do their journeys reshape the galaxy? And what might they reveal about the cosmic dance of stars, planets, and the unseen forces that bind them? The answers lie not only in telescopes and data, but in the boundless imagination of those who dare to dream among the stars. This expansion of the original content adheres to the requested structure, weaving scientific detail with a narrative of cosmic wonder. Each section delves into the trajectory, implications, and broader significance of 3I Atlas, while maintaining a contemplative tone. The transition to the next segment invites further exploration, ensuring continuity in the overarching theme of interstellar discovery. In the vast silent expanse of the cosmos, where time stretches into eons and distances dwarf human comprehension, a solitary traveler approaches. 3I Atlas, an interstellar comet, drifts through the inner solar system, a relic from a distant star's nursery. Discovered on 1 July 2025 by the Atlas Survey Telescope in Chile. This object is not of our solar system. It is a cosmic nomad, born elsewhere in the Milky Way, now passing through our celestial neighborhood, on a trajectory that will carry it back into the abyss of interstellar space. The story of 3I Atlas begins in the cold, dark reaches of another planetary system, where it formed from the primordial material surrounding a long-dead star. Billions of years ago, gravitational chaos, a close encounter with a giant planet, a passing star, or the relentless pull of a binary companion, flung it into the void. Now it arrives at our doorstep, a transient guest in a solar system that is both familiar and alien. Its hyperbolic path, a straight-line escape from the sun's gravity, marks it as a wanderer. With a speed of 58 kilometers per second, it races through the inner solar system, faster than any native comet. Yet, despite its velocity, it poses no threat to Earth, skimming the region between Mars and Earth at a safe distance. This is the third interstellar object ever confirmed, following the enigmatic One-Eye Oumuamua and the more cometary Two-Eye Borisov. But Three-Eye Atlas is unique. Its coma, a glowing halo of gas and dust, reveals a composition unlike any previously studied interstellar object. Rich in carbon dioxide, laced with cyanide and nickel, it carries secrets from a star system we may never see. Its journey, spanning millennia, is a testament to the interconnectedness of galaxies, a reminder that the universe is not a collection of isolated worlds, but a tapestry of shared histories. As Three-Eye Atlas nears its closest approach to the Sun in October 2025, telescopes on Earth and in space turn their gaze toward this fleeting visitor. Scientists watch intently, hoping to decode its origins and understand the forces that forged it. In the quiet hum of its passage, we are reminded of our place in the cosmos, observers of a grand, unfolding story, where every comet, every star is a thread in the infinite weave of existence. To comprehend the journey of Three-Eye Atlas, one must first grasp the violent and elegant dance of planetary systems. Comets, those icy wanderers, are born in the outer reaches of star systems, where temperatures are so frigid that volatile ices freeze into solid form. In these distant realms, comets reside in reservoirs like the Kuiper Belt or the Oort cloud, held in place by the gravitational grip of their host stars. Yet, these are not static realms. They are dynamic, teeming with unseen forces that can unseat a comet from its orbit and hurl it into the void. The ejection of a comet from its home system is a process of cosmic billiards. Picture a planetary system as a chaotic arena, where the gravitational influence of giant planets acts as a slingshot. When a comet ventures too close to a gas giant like Jupiter, the planet's immense gravity can bend the comet's trajectory, accelerating it to escape velocity. This gravitational slingshot effect, akin to a cosmic game of pinball, can propel the comet into interstellar space, forever severed from its birthplace. Alternatively, the passage of a rogue star, or the tidal forces of a binary star system, can perturb the delicate balance of a comet's orbit, nudging it onto a hyperbolic path. For Three-Eye Atlas, the escape likely occurred through one of these mechanisms. Its hyperbolic excess velocity, 58 kilometers per second, suggests a powerful ejection event, one that required a significant gravitational interaction. Computer models indicate that such a speed could result from a close encounter with a massive planet, such as a super Jupiter or a binary star system, where gravitational tides tore the comet from its orbit. The latter scenario is particularly intriguing. Binary systems are common in the Milky Way, and their gravitational instability often births interstellar objects. If Three-Eye Atlas originated in such a system, its journey could be part of a broader pattern, a cosmic exodus of comets cast adrift by the turbulence of stellar nurseries. Yet, the story does not end at ejection. Once free of its home system, the comet enters the interstellar medium, a region of sparse gas and dust, where it travels unimpeded for millennia. During this journey, the comet's nucleus remains dormant, shielded from the sun's warmth by layers of ice. Only when it nears another star system, our own in this case, does it awaken. The sun's heat sublimates its ices, transforming frozen carbon dioxide, water and methane into gas, which in turn lifts dust from the nucleus, creating the luminous coma and tails that mark its presence. This transformation is not merely aesthetic, it is a window into the comet's history. The composition of its coma, rich in CO2 and lacking certain carbon chain molecules, offers clues about the conditions of its birthplace and the processes that shaped it. The mechanics of ejection and reawakening are not unique to Three-Eye Atlas. They are universal phenomena, recurring across the Milky Way. Every interstellar comet that traverses the solar system is a product of these forces, a fragment of a forgotten world, carrying the imprints of its origin. In studying Three-Eye Atlas, we do not merely observe a single object. We trace the echoes of countless planetary systems, each with its own story of creation and destruction. The study of 3I Atlas extends beyond its immediate trajectory and composition. It serves as a Rosetta Stone for understanding the architecture of other planetary systems and the evolutionary processes that govern them. By analyzing its properties, scientists can infer the conditions under which it formed and the forces that shaped its journey. For instance, the comet's rich carbon dioxide contents suggests it originated beyond the CO2 frost line of its parent star, a region where temperatures are low enough for CO2 to condense into solid form. This places 3I Atlas in the outer reaches of its natal system, akin to the Kuiper belt or the scattered disk of our solar system. Moreover, the comet's age, estimated at 7 to 14 billion years, challenges our understanding of the timeline of the Milky Way. If 3I Atlas hails from the galaxy's thick disk, a population of ancient stars with low metallicity, it predates the solar system itself. This raises profound questions. Could such an ancient comet have witnessed the formation of its host star? Did it bear witness to the violent collisions and mergers that sculpted the galactic disk? The answer lies in the isotopic ratios of its volatiles, which may hold a fossil record of the star-forming environment from which it emerged. The absence of carbon chain compounds in 3I Atlas's coma also hints at the chemistry of its birthplace. Unlike many solar system comets, which contain complex organic molecules like polycyclic aromatic hydrocarbons, PAHs, 3I Atlas is strikingly depleted in these substances. This scarcity could reflect the chemical conditions of its parent system, a star-forming region with limited access to the building blocks of life, or the effects of prolonged exposure to cosmic rays, which may have altered its molecular structure. Either possibility underscores the diversity of planetary systems and the myriad ways in which they evolve. Perhaps most compelling is the comet's trajectory. Its path through the solar system is nearly aligned with the ecliptic, the plane of the planet's orbits. This retrograde inclination, tilted 175 dark relative to the ecliptic, is statistically rare among interstellar objects. Such a trajectory suggests that 3I Atlas's ejection was influenced by a force capable of imparting a significant vertical component to its motion. Ampere's binary star system, with its gravitational asymmetry, could have achieved this. Alternatively, a close encounter with a massive object, perhaps a wandering brown dwarf or a rogue planet, might have tilted its path. These scenarios are not mere theoretical exercises. They inform our models of how planetary systems interact and how interstellar objects are distributed throughout the galaxy. Furthermore, the study of 3I Atlas's interactions with the solar system's planets provides insights into the dynamics of interstellar encounters. Its close approach to Mars in October 2025 offers an opportunity to observe how a comet behaves in the gravitational field of a terrestrial planet. Will Mars's weak gravity perturb its trajectory? Will the comet's coma interact with the planet's thin atmosphere? These questions are not purely academic. They help us predict the behavior of future interstellar visitors and assess the potential for contamination or resource exchange between star systems. Even the debate over 3I Atlas's nature, a comet or something more, highlights the boundaries of our knowledge. While the overwhelming consensus among astronomers is that it is a natural object, the speculation that it could be an artificial construct, as proposed by Avi Loeb and others, serves as a reminder of the limits of our current understanding. The detection of nickel and cyanide in its coma, while consistent with cometary outgassing, has sparked curiosity about the role of exotic materials in interstellar objects. Future observations, particularly those using the James Webb Space Telescope and ground-based interferometers, will refine our knowledge of its composition and resolve lingering uncertainties. In essence, 3I Atlas is more than a passing curiosity. It is a messenger from the depths of the galaxy, bearing the fingerprints of a star system we may never visit. Its study bridges the gap between planetary science and galactic astronomy, offering a glimpse into the universal processes that shape worlds and scatter their remnants across the cosmos. As 3I Atlas continues its journey beyond the sun's reach, its story merges with the broader narrative of cosmic connectivity. Though born in a distant system, it shares kinship with the comets of our own solar system, revealing that the mechanisms of formation and ejection are not unique to any one star. The same gravitational slingshots, the same icy nuclei, the same volatile outgassing, all echo the processes that birthed Halley's Comet and the Oort cloud. This universality suggests that interstellar comets are not anomalies, but inevitable byproducts of planetary evolution. Yet 3I Atlas's journey also underscores the rarity of such encounters. For every comet that escapes its system, countless others remain bound to their stars, their fates sealed by the gravitational embrace of planets. The fact that 3I Atlas reached our skies at all is a stroke of cosmic fortune, a confluence of timing and trajectory that allows us to glimpse the lives of distant worlds. As it departs, it leaves behind more questions than answers. How many interstellar comets have silently passed through the solar system unnoticed? What secrets lie in their frozen cores, waiting to be uncovered? And what else beyond comets might drift unseen through the galactic dark? The exploration of 3I Atlas is but the beginning. With next-generation telescopes and dedicated missions, humanity stands on the precipice of a new era in interstellar science. Perhaps one day, a probe will chase a comet like this, tracing its path back to its home. Until then, 3I Atlas remains a beacon, a reminder that the universe is vast, interconnected, and full of stories waiting to be told. In the vast, silent expanse of the cosmos, where time stretches into epochs and space folds into infinity, a solitary traveler emerged from the depths of interstellar darkness. Discovered on 1 July 2025 by the asteroid Terrestrial Impact Last Alert System, Atlas in the arid skies of Chile, 3I Atlas, a comet born in a distant stellar cradle, arrived at the doorstep of our solar system. Its arrival was not a whisper but a declaration. I am here, and I am not from here. This interstellar wanderer, the third confirmed visitor from beyond our planetary neighborhood, after 1I Oumuamua and 2I Borisov, carries secrets etched in stardust, ice, and the echoes of ancient starlight. As 3I Atlas glides through the inner solar system, its hyperbolic trajectory, a path bent by the sun's gravity, yet unbound by it, marks it as a transient guest. Moving at a blistering 58 kilometers per second, 36 ms, faster than any interstellar object before it, it defies the gravitational embrace of our star, destined to vanish into the cosmic void. Yet in its fleeting passage, it offers a rare opportunity, a glimpse into the chemistry of another world, a snapshot of conditions in a star system light years away. What stories does this comet tell? What truths does it carry, frozen in its nucleus, waiting to be deciphered? To understand 3I Atlas is to peer into the heart of the Milky Way, to trace the origins of a body that predates our solar system by billions of years. Its journey began in the thick disk of our galaxy, a region where ancient stars drift in quiet orbits, their light dimmed by the passage of eons. Here, in a realm where time itself seems to stretch, 3I Atlas was born, a relic of a long-lost protoplanetary disk, cast adrift by the gravitational tides of a distant star. Now, as it hurtles past Mars and Venus, it invites us to ponder the universality of cometary formation, the shared origins of planetary systems, and the possibility that life's building blocks are scattered across the cosmos like seeds on the wind. This is not merely the story of a comet, it is a testament to the interconnectedness of the universe, a reminder that we are but one thread in a tapestry woven by the hands of time and gravity. Let us embark on this journey with 3I Atlas, tracing its path from discovery to departure, unraveling its mysteries, and contemplating the profound questions it awakens in our hearts. At its core, 3I Atlas is a paradox, a fragile yet resilient object forged in the crucible of a distant star's birth. Its nucleus, a solid icy body shrouded in a coma of gas and dust, is a time capsule of primordial material. As sunlight warms its surface, volatile ices sublimate into vapor, carrying with them particles of dust and organic compounds. This process, known as cometary activity, gives rise to the comet's luminous coma, and the delicate tails that trail behind it like whispers of its past. The Hubble Space Telescope's observations revealed that 3I Atlas's nucleus is likely less than 1 kilometer in diameter, a modest size compared to the colossal worlds of the solar system. Yet its true power lies in its composition. Spectroscopic analysis conducted by the James Webb Space Telescope, JWST, unveiled a startling truth. 3I Atlas is unusually rich in carbon dioxide, CO2, with a CO2 to water ratio 8 times higher than typical solar system comets. This abundance suggests that it formed far from its parent star, beyond the CO2 frost line, where temperatures are low enough for the gas to condense into ice. Such a location implies a formation history akin to the Kuiper belt or Oort cloud of our own system. Yet with a twist, perhaps the chemistry of its parent star's protoplanetary disk was richer in CO2, or perhaps interstellar travel has altered its volatile balance. The comet's activity is not static. As 3I Atlas approaches perihelion, the closest point to the Sun, it accelerates, heating up and releasing more gas and dust. By July 2025, even at a distance of 4.5 AU from the Sun, it was already active, its coma glowing with the faint red hues of irradiated organic compounds. This early activation, observed by NASA's Transiting Exoplanet Survey satellite, TESS, hints at the presence of volatile ices beyond water, such as carbon monoxide and methane, which sublimate at lower temperatures. The Very Large Telescope MALE-T later confirmed the presence of cyanide gas and atomic nickel in its coma, substances typically associated with the thermal decomposition of complex organic molecules. These findings challenge our understanding of cometary chemistry, suggesting that interstellar comets may harbor unique molecular signatures shaped by their parent system's environments. Yet for all its activity, 3I Atlas remains elusive. Its nucleus, obscured by a veil of dust, resists direct observation. The JWST's infrared gaze pierced this veil, estimating the nucleus's diameter between 0.32 and 5.6 kilometers, but uncertainties persist. The coma itself is a dynamic entity, expanding and evolving as the comet interacts with solar radiation. By August 2025, its coma spanned over 348,000 kilometers in radius, a domain of gas and dust, stretching farther than the distance from Earth to the Moon. Within this cloud, particles of varying sizes behave differently. Microscopic grains are swept away by solar winds, while larger grains linger closer to the nucleus, forming a sun-facing plume. This phenomenon, captured in Hubble images, reveals the asymmetry of cometary activity, a dance of physics choreographed by the Sun's relentless pull. The comet's trajectory, a hyperbolic arc with an eccentricity of 6.141, underscores its extraterrestrial origin. Unlike the elliptical paths of native solar system comets, which loop back into the abyss of space, 3I Atlas's path is a straight-line escape. Its velocity, 58 kilometers per second relative to the Sun, is so great that no planetary encounter could have imparted such speed. Instead, it must have originated from the gravitational chaos of another star system, ejected by the gravitational slingshot of a giant planet or a binary star's tug. This trajectory also aligns with the galactic plane, suggesting that 3I Atlas hails from the Milky Way's thick disk, a population of ancient stars whose motions trace the galaxy's evolutionary history in every detail of its anatomy. 3I Atlas is a bridge between worlds. Its nucleus holds the legacy of a protoplanetary disk, long since dispersed. Its coma sings of interstellar chemistry, and its path whispers of the cosmic currents that shaped its journey. To study it is to trace the threads of a tapestry woven across galaxies, where each comet is a stitch in the fabric of existence. The discovery of 3I Atlas compels us to reconsider the universality of cometary formation. For centuries, comets in our solar system have been viewed as relics of the early protoplanetary disk, their icy nuclei preserving the primordial materials from which planets coalesced. Yet 3I Atlas, born in a star system billions of years older than our own, challenges this notion. Its CO2-rich coma, absent the high water content typical of solar system comets, suggests that the recipe for comet making varies across the galaxy. Does this mean that comets are as diverse as the stars that forge them, or does it hint at a deeper cosmic consistency? The answer may lie in the chemistry of its parent star. If 3I Atlas indeed originates from the thick disk of the Milky Way, its parent star would have formed in an era when the galaxy was younger and enriched with fewer heavy elements. Such a star's protoplanetary disk would have had a different chemical signature, one where CO2 dominated over water ice. This scenario implies that comets are not uniform across the cosmos, but reflect the unique histories of their stellar nurseries. Alternatively, the comet's CO2 abundance could be a product of interstellar travel itself. As 3I Atlas traversed the galaxy for eons, exposure to cosmic rays and stellar radiation may have altered its surface chemistry, masking its original composition. Yet, despite these differences, 3I Atlas shares striking similarities with its solar system counterparts. Its reddish coma, composed of large organic-rich dust grains, mirrors the spectral profiles of D-type asteroids and the interstellar comet 2I Borisov. The presence of cyanide, nickel, and water vapor in its coma further reinforces the idea that certain molecular building blocks, those essential for life, are widespread in the galaxy. These findings suggest a dual reality. While the specifics of cometary chemistry may vary, the underlying principles of planetary formation are universal. This duality has profound implications for astrobiology. If comets like 3I Atlas carry the same organic molecules found in solar system comets, they may serve as cosmic couriers, seeding nascent planetary systems with the ingredients for life. The Milky Way, teeming with interstellar comets, could be a vast reservoir of biologically relevant compounds, scattering them across the cosmos like stardust in a galactic wind. Yet 3I Atlas's uniqueness also raises questions. Could its chemistry be incompatible with life as we know it? Or does its very diversity expand the possibilities for alternative biochemistries? The study of 3I Atlas is thus a window into the origins of life itself. Its CO2-rich nucleus may not support Earth-like biology, but it could harbor exotic chemical pathways, thriving in conditions we scarcely imagine. By analyzing its molecular inventory, we gain insight into the versatility of life's building blocks and the adaptability of chemistry in the face of cosmic extremes. In this sense, 3I Atlas is not just a comet, it is a cosmic laboratory, a testament to the ingenuity of nature in forging complexity from simplicity. Yet, for all its revelations, 3I Atlas remains a mystery. Why does it emit nickel vapor but not iron? Why is its carbon chain chemistry so depleted compared to solar system comets? These questions underscore the limits of our knowledge, the gaps in our understanding of interstellar objects. They also highlight the importance of continued observation. As 3I Atlas approaches perihelion, the James Webb Space Telescope and Hubble will continue to dissect its coma, seeking answers hidden in its spectral lines. Each data point brings us closer to unraveling the comet's secrets and to answering the question that haunts every explorer of the cosmos: are we alone? Tracking 3I Atlas is a race against time. As it races toward perihelion, its solar elongation shrinks, reducing its visibility to equatorial observers just after sunset. By October 2025, it will vanish behind the sun, lost to Earth-based telescopes. Yet, its journey is not over. Mars orbiters will catch glimpses of the comet as it passes within 0.19 AU of the red planet, and the James Webb Space Telescope will continue its vigil from afar. These observations will shape our understanding of interstellar comets, but they also highlight the fragility of our connection to the cosmos. The tools we use, telescopes perched on mountaintops, space observatories suspended in orbit, are extensions of our curiosity, our yearning to touch the unreachable. Yet they are limited by the very nature of the universe. Distance, time, and the ephemeral lives of cosmic travelers. 3I Atlas will depart the solar system by March 2026, carrying with it the whispers of a star system we may never see. But in its wake, it leaves a legacy of questions, a call to refine our instruments and expand our horizons. In the vast expanse of the cosmos, where interstellar travelers, like 3I Atlas, traverse the void at velocity exceeding 58 kilometers per second. Humanity's ability to study such fleeting visitors hinges on a tapestry of technological ingenuity. To unravel the mysteries of this speeding comet, a frozen relic from another star system, requires a symphony of instruments spanning the globe and beyond, from the icy peaks of Chile to the orbit of the James Webb Space Telescope, from the deserts of Arizona to the Martian skies. Humanity's gaze is fixed on this enigmatic wanderer. The challenge is immense. 3I Atlas is faint, moving rapidly, and will soon vanish from view as it slingshots out of the solar system. Yet through the collective efforts of ground-based observatories, space telescopes, and robotic explorers, we strive to decode its origins, its chemistry, and its trajectory. This is not merely an act of observation, but a testament to our species' relentless curiosity and capacity to unite science, technology, and imagination in the face of the unknown. The study of 3I Atlas is a triumph of modern astronomy, a field that has evolved from solitary stargazers peering through rudimentary lenses to a global network of automated surveys and spacefaring machines. The comet's discovery by the Asteroid Terrestrial Impact Last Alert System, ATLAS, marked the first step in a cascade of observations that would involve dozens of telescopes and spacecraft. Ground-based facilities, such as the Hubble Space Telescope, the Very Large Telescope, VLT, and the Gemini South Telescope, have played pivotal roles in mapping 3I Atlas's coma, measuring its dust distribution, and analyzing its chemical composition. Hubble's high-resolution imaging has constrained the nucleus's size to less than 5.6 kilometers, while the VLT's spectroscopic prowess has detected cyanide and nickel vapor, gases rarely observed in such quantities outside the solar system. Above Earth, the James Webb Space Telescope, JWST, has revolutionized our understanding of 3I Atlas's icy heart. With its infrared capabilities, JWST pierced the veil of dust surrounding the comet, revealing a coma rich in carbon dioxide, a finding that defies expectations for objects so far from the Sun. The Transiting Exoplanet Survey Satellite, TESSI, designed to hunt for alien worlds, unexpectedly captured 3I Atlas in its early stages of activity, confirming that the comet was already shedding material at distances where water ice alone should not have been active. Meanwhile, the Swift Observatory, optimized for gamma-ray bursts, detected traces of water vapor and hydroxide ions, offering clues about the comet's internal dynamics. Even Mars, a planet millions of kilometers away, may play a role in this cosmic detective work. As 3I Atlas passes within 0.19 AU of the Red Planet, in late October 2025, orbiters like NASA's Mars Reconnaissance Orbiter and ESA's Mars Express could capture unprecedented close-up views. These spacecraft, originally tasked with studying Martian geology and climate, now serve as accidental sentinels, their cameras and spectrometers trained on a visitor from another stellar neighborhood. The adaptability of these instruments underscores the versatility of modern space exploration, where every mission carries the potential for serendipitous discoveries. Yet the study of 3I Atlas is not solely the domain of professional astronomers. Amateurs with backyard telescopes and plate-solving software have contributed critical observations, filling gaps in the comet's orbital history and tracking its subtle changes in brightness. Their efforts highlight the democratization of science, where citizen scientists and seasoned researchers collaborate to piece together the story of an interstellar traveler. This global network of eyes and ears ensures that no detail is overlooked, no anomaly goes unnoticed. The technological marvels that track 3I Atlas are more than tools. They are extensions of human ingenuity, bridging the gap between the tangible and the infinite. They remind us that our quest to understand the universe is not confined to Earth, but is a shared endeavor, transcending borders and disciplines. The collaboration between ground-based and space-based observatories, between professional and amateur astronomers, reflects a profound truth. Knowledge is a collective pursuit, illuminated by the combined light of countless minds. However, the study of 3I Atlas also reveals the limitations of our current capabilities. Despite the wealth of data gathered, many questions remain unanswered. What exactly triggered the comet's hyperbolic trajectory? Why does its coma glow with such a high concentration of carbon dioxide? What secrets lie beneath its insulating crust? These uncertainties underscore the need for future missions, designed specifically to interstellar visitors. Concepts like NASA's Interstellar Probe, or proposals for dedicated interstellar cometary missions, envision spacecraft capable of matching the speed and distance of objects like 3I Atlas, enabling direct sampling of their ices and dust. Such endeavors would not only deepen our understanding of cometary science, but also shed light on the conditions prevalent in other star systems, expanding our cosmic perspective. Moreover, the fleeting nature of 3I Atlas's passage serves as a humbling reminder of our place in the universe. Unlike planets or stars, which remain fixtures in the night sky for millennia, interstellar objects are transient phenomena, cosmic messengers that arrive unannounced and depart before we can fully grasp their significance. 3I Atlas's 58 kilometers per second velocity, faster than any known interstellar object before it, ensures that it will escape the solar system within months, leaving behind only data and questions. Yet, in its brief encounter with our corner of space, it has already transformed our understanding of the galaxy. Its CO2-rich coma, its nickel-laden tail, and its retrograde orbit offer glimpses into the chaotic dance of matter and energy in the Milky Way, a dance that has shaped the birth and death of stars for billions of years. The implications extend beyond science. 3I Atlas challenges our assumptions about the uniqueness of our solar system. If such objects are common, traveling freely between stars, carrying the chemical fingerprints of their home systems, then the universe is far more interconnected than we once imagined. Every interstellar comet is a bridge between stellar nurseries, a record of the cosmic crucible where planets and life may have taken root. In studying 3I Atlas, we are not merely observing a distant fragment of ice and rock. We are tracing the threads of a galactic tapestry, woven from the debris of ancient stars and the raw materials of worlds yet to be born. Yet for all its scientific revelations, 3I Atlas remains an enigma. Its anomalous traits, its high velocity, its alignment with the ecliptic, its unusual chemical signature have sparked debates that stretch beyond the confines of conventional astrophysics. Some have speculated that this object is not a natural phenomenon, but a construct of intelligence, a vessel or artifact from an alien civilization. Such hypotheses, though controversial, are not dismissed outright by the scientific community. Rather, they are met with rigorous scrutiny, demanding extraordinary evidence to support extraordinary claims. As 3I Atlas continues its journey, the line between the known and the unknowable blurs, inviting us to consider possibilities that lie at the edge of our understanding. The next segment delves into the provocative theories surrounding 3I Atlas's true nature, exploring the intersection of science, speculation, and the enduring human desire to find meaning in the stars. In the vast expanse of the cosmos, where stars flicker like distant sentinels and galaxies spiral in silent majesty, a new visitor has emerged, discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, ATLAS. In Chile, 3I Atlas stands as a testament to the ever-unfolding story of the universe. This interstellar comet, hurtling through the inner solar system at an astonishing speed of 58 kilometers per second, carries with it the secrets of its distant origins. Unlike the countless comets born within our own celestial neighborhood, 3I Atlas does not belong here. It is a traveler from another star system, a fragment of an alien world now passing through our cosmic backyard. Its arrival stirs profound questions. Where did it come from? What forces shaped its journey? And what can it teach us about the nature of the universe itself? As it glides through the void, its icy nucleus shedding gas and dust in a luminous coma, it reminds us that we are not alone in the cosmos, and that the universe is a tapestry woven with countless stories waiting to be unraveled. The discovery of 3I Atlas adds to the growing catalogue of interstellar objects that have graced our skies. Following the enigmatic 1I Oumuamua in 2017, and the more recent 20I Borisov in 2019, this comet represents the third confirmed visitor from beyond our solar system. Yet, unlike its predecessors, 3I Atlas exhibits distinct cometary activity, its nucleus releasing clouds of gas and dust as it interacts with the sun's radiant energy. This dynamic transformation offers a rare glimpse into the processes that govern comets in other planetary systems, providing clues about the conditions under which they formed. With its hyperbolic trajectory, a path that ensures it will never return, 3I Atlas is a fleeting guest, destined to vanish beyond the reach of our telescopes. Still, its brief passage through the inner solar system presents an opportunity to study the chemistry, composition, and behavior of a celestial body that originates from a distant corner of the galaxy. Through meticulous observation and analysis, scientists hope to unlock the mysteries hidden within its icy depths, unraveling the threads of cosmic history that connect our world to the stars. As 3I Atlas continues its journey, it serves as a reminder of the vastness of space and the endless possibilities it holds. Though it will never pose a threat to Earth, its mere existence challenges our understanding of the universe's interconnectedness. The comet's trajectory, traced back through the night sky, reveals that it came from the direction of the constellation Sagittarius, near the heart of the Milky Way. Could it have originated from a star system nestled within the dense stellar nurseries of that region? Or perhaps it was ejected from a distant planetary system long ago, embarking on a solitary voyage through the galaxy? These questions echo the fundamental curiosity that drives human exploration, urging us to look beyond the familiar and seek answers among the stars. In the quiet solitude of deep space, 3I Atlas moves forward, a silent emissary of the cosmos, carrying with it the echoes of worlds unseen and histories untold. The moment of discovery for 3I Atlas was as dramatic as it was fortuitous. On 1 July 2025, the Atlas Survey telescope at Rio Hurtado, Chile, captured the first glimpse of this interstellar traveler. At the time of its detection, the comet was situated at a distance of 4.5 astronomical units, AU, from the Sun, or approximately 670 million kilometers. Moving at a staggering speed of 61 kilometers per second, 3I Atlas was already deep within the inner solar system, yet its true nature remained shrouded in mystery. The object's initial classification was uncertain. Was it an asteroid, a comet, or something entirely unfamiliar? The ambiguity stemmed from its trajectory and the challenges posed by its position near the galactic center, where the dense star fields obscured its visibility. As the Atlas team submitted their observations to the International Astronomical Union's Minor Planet Center, MPC, the object was temporarily designated A11PL3Z, while further observations sought to clarify its identity. What set 3I Atlas apart from ordinary solar system objects became evident as follow-up observations poured in from observatories around the world. Professional and amateur astronomers alike contributed to refining the comet's trajectory, revealing its hyperbolic path, a telltale sign of an interstellar origin. The hyperbolic trajectory meant that 3I Atlas was not gravitationally bound to the Sun, and its velocity exceeded the escape velocity of the solar system. This distinction placed it in a rare category of celestial bodies, joining the ranks of 1I Oumuamua and 2I Borisov as the third confirmed interstellar object. The confirmation was a triumph of collaborative science, with pre-discovery observations from the Zwicky Transient Facilities (ZTF) and other telescopes tracing the comet's path back to late May 2025. The data painted a picture of an object hurtling through space at a speed that defied the gravitational constraints of our own system, a visitor from the depths of the galaxy. As more observations accumulated, the nature of 3I Atlas began to take shape. Initially, its status as a comet was uncertain. The absence of a visible coma or tail left some astronomers questioning whether it was an asteroid. However, by mid-July 2025, the Deep Random Survey X09 at Chile, the Lowell Discovery Telescope G37 in Arizona, and the Canada-France-Hawaii Telescope T14 on Mauna Kea all detected a faint, diffuse glow surrounding the object. This glow, combined with a subtle elongation of 3 arcseconds in angular length, confirmed that 3I Atlas was indeed a comet, actively shedding material in response to the Sun's heat. The discovery was officially announced by the MPC on 2 July 2025, marking the comet's designation as CES 2025 N1 Atlas and its classification as an interstellar object with the prefix 3I. By the time of its formal naming, the MPC had compiled 120 observations from 31 different observatories, a testament to the global effort to understand this cosmic wanderer. The confirmation of 3I Atlas as an interstellar comet ignited a wave of excitement and curiosity within the scientific community. Unlike 1I Oumuamua, which exhibited no signs of cometary activity, 3I Atlas displayed the characteristic features of a comet, its nucleus releasing gas and dust as it approached the Sun. The presence of a coma and the detection of sublimating ices indicated that 3I Atlas was composed of volatile materials, much like the comets of our own solar system. Yet its interstellar origin raised intriguing questions about its formation and history. Had it been ejected from a distant planetary system, or did it originate from a stellar nursery where comets are born in abundance? The answers to these questions lay in the detailed analysis of its trajectory, composition, and behavior as it continued its journey through the inner solar system. As 3I Atlas traverses the inner solar system, its trajectory paints a grand arc of motion dictated by the Sun's gravitational pull. The comet's hyperbolic path ensures that it is not bound to our system, and its velocity, exceeding the escape velocity of the solar system, guarantees that it will eventually depart, continuing its journey into the vast interstellar void. The comet's speed relative to the Sun, known as its hyperbolic excess velocity, is an impressive 58 kilometers per second, 36 miles per second, making it the fastest interstellar object observed to date. This speed surpasses that of both 1I Oumuamua, 26 kilometers per second, and 2I Borisov, nor 32 kilometers per second, reinforcing the notion that 3I Atlas is a rare and energetic visitor from the depths of the galaxy. As it draws closer to the Sun, the comet accelerates, reaching its maximum velocity of 68 kilometers per second at perihelion, the point in its trajectory where it is closest to the Sun. This acceleration is a direct consequence of the Sun's gravitational influence, which pulls the comet inward before it ultimately slingshots outward once more. The orbital eccentricity of 3I Atlas is a defining characteristic of its interstellar nature. Whereas the elliptical orbits of solar system comets and planets have eccentricities less than 1, 3I Atlas possesses an extremely high eccentricity of 6.141 NOS 0.02. This value places it among the most extreme trajectories observed in the cosmos, with its path appearing nearly straight rather than curved. The high eccentricity also indicates that the comet is not influenced by any planetary perturbations within the solar system. Unlike 1I Oumuamua, in a false pulse, E3.4, 3I Atlas's trajectory is the most hyperbolic of the three interstellar objects known to date. This trajectory suggests that 3I Atlas's origin lies beyond the gravitational reach of any known planetary system, and its path is dictated solely by the dynamics of the Milky Way. As 3I Atlas approaches its closest approach to the Sun, on 29 October 2025, it will reach a perihelion distance of 1.36 AU, 23 million kilometers, a point that lies between the orbits of Earth and Mars. At this moment, the comet will be at its most active, with the Sun's intense radiation sublimating ices from its nucleus and driving the release of gas and dust. Despite its proximity to the inner planets, 3I Atlas will not pose a threat to Earth. Its closest approach to our planet will occur on 19 December 2025, at a safe distance of 1.8 AU 2069 million kilometers. The comet will also pass relatively near to Venus and Mars, 0.65 AU 97 million kilometers, from Venus on 3 November 2025, and 0.19 AU 28 million kilometers, from Mars on 3 October 2025. These encounters provide opportunities for detailed observations, particularly for Mars-orbiting spacecraft, which may capture images of the comet as it passes by the red planet. The trajectory of 3I Atlas is not only remarkable for its speed and eccentricity, but also for its alignment with the ecliptic, the plane defined by the orbits of the solar system's planets. The comet's orbital inclination is 175 degrees, meaning that its path is retrograde and inclined by 5 degrees relative to the ecliptic. This orientation allows it to intersect the paths of multiple planets, though it remains far enough from them to avoid any significant gravitational interactions. The retrograde motion of 3I Atlas, moving in the opposite direction to the majority of solar system objects, further underscores its interstellar origin. While most comets within our system originate from the Kuiper belt or the distant Oort cloud and follow prograde orbits, the retrograde nature of 3I Atlas suggests that it was born in a different stellar environment, where gravitational interactions may have imparted a unique trajectory. As the comet continues its journey, it will eventually exit the inner solar system, departing in the direction of the constellation Lyra. From our vantage point on Earth, 3I Atlas will remain a faint object, not expected to reach a brightness sufficient for naked eye visibility. Its peak brightness is projected to be around apparent magnitude 11.5, making it detectable only with telescopes. The comet's dimness is a result of its relatively small nucleus and the fact that it will not pass close enough to the Sun to produce a brilliant display like that of Halley's Comet or Comet Neowise. Nevertheless, the scientific value of 3I Atlas remains immense. Its passage through the inner solar system offers a rare opportunity to study an interstellar comet in detail, providing insights into the composition and evolution of celestial bodies in other planetary systems. As it vanishes into the depths of space, 3I Atlas leaves behind a trail of data and unanswered questions, inviting further exploration into the mysteries of the cosmos. As 3I Atlas journeys through the inner solar system, its dynamic interaction with the Sun reveals a wealth of information about its composition and behavior. Like all comets, 3I Atlas consists of a solid nucleus composed primarily of ice and rock, encased in a diffuse coma of gas and dust. The Sun's radiant energy heats the comet's nucleus, causing volatile ices to sublimate directly into gas, a process that propels dust particles outward and creates the glowing coma. This activity is not uniform across the comet's surface. Instead, it is concentrated in regions where the sublimation of ices is most intense. The resulting outflow of gas and dust forms a complex and evolving structure, with distinct features such as the sun-facing dust plume and the faint anti-solar tail. Observations from the Hubble Space Telescope in July 2025 captured the intricate details of 3I Atlas's coma, revealing a cloud of gas and dust that extends tens of thousands of kilometers from its nucleus. The size and density of the coma grow as the comet approaches the Sun, indicating an increase in its activity. By the time 3I Atlas reaches perihelion, its coma is expected to span hundreds of thousands of kilometers, a testament to the Sun's powerful influence on this interstellar visitor. One of the most striking features of 3I Atlas is its sun-facing dust plume, a region of enhanced dust emission that stretches toward the Sun and the direction of the comet's motion. Unlike a traditional comet tail, which is oriented away from the Sun, this plume is a result of localized heating on the comet's surface, where ice sublimates rapidly and ejects dust at high speeds. The plume's elongated shape suggests that the comet's rotation plays a role in directing the outflow of material, possibly due to variations in the surface topography or the distribution of volatile ices. This phenomenon is not unique to 3I Atlas. Similar sun-facing features have been observed in other distant comets, such as CEAS 2014, UN 271, Bernard and Ellie Bernstein. However, the prominence of the plume in 3I Atlas indicates a particularly active and dynamic surface, where the interplay of heat and volatile materials generates a continuous stream of ejected dust. The plume's presence also implies that 3I Atlas's nucleus is not uniformly composed, but rather contains pockets of ice that sublimate at different rates depending on their exposure to solar radiation. Beyond the sun-facing plume, the anti-solar tail of 3I Atlas provides additional insight into the comet's activity. Observed by the Hubble Space Telescope in July 2025, the tail is a faint, broad feature that points directly away from the Sun. Unlike the plume, which is driven by localized heating, the tail is formed by the cumulative effect of solar radiation pressure on the comet's dust particles. Smaller grains, accelerated by the Sun's photons, are carried outward in a streaming motion, forming a diffuse and expansive tail that can extend millions of kilometers. The tail of 3I Atlas is expected to become more prominent as the comet approaches perihelion, with the increased solar heating driving a higher rate of dust emission. The tail's composition and structure will offer valuable clues about the physical properties of the comet's surface and the mechanisms governing its activity. By analyzing the tail's spectral signature, scientists hope to determine the types of ices and minerals present in 3I Atlas's nucleus, further enriching our understanding of its interstellar origins. The chemical composition of 3I Atlas is another crucial aspect of its study, as it provides direct evidence of the materials that exist in other planetary systems. Spectroscopic analyses conducted by the James Webb Space Telescope, JWST, and the FEREX mission have revealed that the comet's coma is unusually rich in carbon dioxide, CO2, with smaller quantities of water ice, water vapor, carbon monoxide, CO, and carbonyl sulfide, OCS. The high CO2 abundance is particularly intriguing, as it deviates from the typical composition of solar system comets, which tend to have lower CO2 to water ratios. This discrepancy suggests that 3I Atlas may have formed in a different environment, where CO2 was more readily available, or where the conditions favored its preservation. The presence of CO2 also implies that the comet's nucleus contains a significant reservoir of this volatile substance, which sublimates as the comet approaches the Sun and contributes to the coma's expansion. The detection of water ice and water vapor further supports the idea that 3I Atlas shares similarities with comets in our own system, despite its interstellar origin. In addition to CO2 and water, the coma of 3I Atlas contains trace amounts of carbon monoxide and carbonyl sulfide, two molecules that are rarely observed in cometary activity. Carbon monoxide, like CO2, is a volatile compound that sublimates at relatively low temperatures, making it a useful indicator of the comet's thermal history. The detection of carbonyl sulfide is particularly notable, as it is a complex organic molecule that may play a role in the formation of prebiotic compounds. The presence of these substances in 3I Atlas's coma suggests that the comet's nucleus contains a diverse mix of ices and organic materials, some of which may have been preserved since the early days of its parent star system. As the comet continues its journey, further spectroscopic observations will provide a more detailed inventory of its chemical composition, shedding light on the processes that shaped its formation and evolution. The activity of 3I Atlas is not limited to the release of gas and dust. The comet also emits trace amounts of cyanide, CN, and atomic nickel, Ni, vapor. These emissions were first detected by the Very Large Telescope, VLT, in July and August 2025, with subsequent observations confirming their presence in the comet's coma. The emission of cyanide is a common feature in comets, as it is often produced by the breakdown of organic compounds under the influence of solar radiation. The detection of atomic nickel, however, is less frequent and presents an intriguing puzzle for scientists. While nickel is typically found in comets alongside iron, no iron emission was detected in 3I Atlas, raising questions about the nature of the nickel source. One possibility is that the nickel is released through the decomposition of nickel-containing organic compounds, a process that may be facilitated by space weathering. The absence of iron suggests that 3I Atlas may have a metal-poor composition, distinguishing it from many solar system comets. As research continues, the role of these emissions in shaping the comet's behavior and chemical evolution will become clearer, offering new insights into the diversity of interstellar comets. Through the study of 3I Atlas's composition and activity, scientists are gaining unprecedented access to the conditions that exist in distant star systems. The comet's unusual chemical profile, its dynamic surface features, and its response to solar heating all contribute to a growing understanding of the processes that govern the formation and evolution of comets in the universe. As 3I Atlas continues its journey through the inner solar system, each observation brings us closer to unraveling the mysteries of this interstellar traveler, revealing the hidden connections between our world and the vast expanse of the cosmos. The origin of 3I Atlas is a question that resonates deeply with the fundamental mysteries of the cosmos. Unlike the comets and asteroids that populate our solar system, which trace their histories to the Kuiper Belt or the distant Oort cloud. 3I Atlas hails from a vastly different and distant realm. Its trajectory, velocity, and chemical composition all point to an interstellar birthplace. Yet pinpointing its precise origin remains a challenge. By analyzing the comet's hyperbolic excess velocity and its trajectory relative to the Milky Way, the data suggests that 3I Atlas entered the solar system from the direction of the constellation Sagittarius, near the galactic center, a region teeming with stars, molecular clouds, and the remnants of ancient stellar nurseries. However, the vast distances involved and the chaotic nature of interstellar space make it impossible to trace the comet back to a specific star system or planetary environment. Instead, 3I Atlas appears to be a relic of a bygone era, a fragment of a distant world that was ejected into the interstellar void long ago. What sets 3I Atlas apart from the previous interstellar visitors, 1I Oumuamua and 2I Borisov, is its apparent origin from the southern celestial hemisphere. Both 1I Oumuamua and 2I Borisov were detected coming from the direction of the solar apex, the region of the sky toward which the sun is moving relative to nearby stars. This alignment was expected, as telescopes on Earth are more likely to detect objects arriving from the solar apex due to the sun's motion through the galaxy. However, 3I Atlas's trajectory diverges from this pattern, originating from a direction that is opposite to the solar apex. This unexpected origin has sparked renewed interest in the distribution of interstellar objects and the possibility that southern origin comets may be more abundant than previously assumed. The discovery of 3I Atlas challenges existing models of interstellar object detection, suggesting that our observational biases may have limited our ability to detect objects from certain regions of the sky. As more interstellar comets are discovered, a clearer picture of their spatial distribution will emerge, offering insights into the dynamical history of the galaxy and the processes that govern the ejection of objects from planetary systems. The age of 3I Atlas is another enigma that captivates astronomers. Determining the age of an interstellar object is no simple task, as it requires understanding its trajectory through the galaxy and estimating how long it has been traveling independently. By examining the vertical component of 3I Atlas's velocity, which measures its motion perpendicular to the galactic plane, scientists have deduced that it belongs to either the thin disk or the thick disk population of the Milky Way. The thin disk, which contains younger stars with higher metallicity, is home to the majority of the galaxy's current stellar population. In contrast, the thick disk is composed of older stars with lower metallicity, some of which date back to the early formation of the galaxy. Given that 3I Atlas's vertical velocity is significantly higher than those of nearby stars, it is likely a member of the thick disk, implying that it has been traveling through the galaxy for an extended period. Amper's study, led by Matthew Hopkins and collaborators in July 2025, estimated with 68% confidence that 3I Atlas is between 7.6 and 14 billion years old. If this estimate is correct, 3I Atlas in the early history of the Milky Way, a time when the galaxy was still forming and its stellar population was in flux. The implications of 3I Atlas's age are profound. If the comet is indeed over 7 billion years old, it may have originated in a different galactic environment than the stars we see today. The early Milky Way was a denser and more chaotic place, with frequent stellar interactions and mergers shaping the distribution of matter. In such an environment, the ejection of comets and other small bodies would have been more common, as gravitational perturbations from passing stars and massive molecular clouds could have stripped planetary systems of their outermost members. The survival of 3I Atlas over such an immense timescale speaks to the resilience of interstellar comets and their ability to endure the harsh conditions of the galactic void. Moreover, its chemical composition, particularly its high abundance of carbon dioxide, may reflect the primordial conditions of its parent star system. If 3I Atlas formed in a different galactic environment, its makeup could provide a snapshot of the chemical diversity that existed in the early universe, offering a unique window into the building blocks of life in other planetary systems. As 3I Atlas continues its journey through the solar system, its origin and age remain subjects of intense study. The comet's trajectory, composition, and dynamical history all contribute to a broader understanding of the interstellar medium and the mechanisms that shape the evolution of planetary systems. While many questions remain unanswered, the discovery of 3I Atlas underscores the vastness of the cosmos and the infinite possibilities that lie beyond our own backyard. As we track its passage, we are reminded that we are but one small part of a universe teeming with wonders, each interstellar object a message from the depths of time and space. The formation of 3I Atlas is a tale written in the chemistry of its composition and the dynamics of its journey through the galaxy. Unlike the comets of our own solar system, which formed within the protoplanetary disk that surrounded the young sun, 3I Atlas must have originated in a different stellar environment. The high abundance of carbon dioxide, CO2, in its coma, for instance, suggests that it formed beyond the CO2 frost line of its parent star system, a region where temperatures are low enough for CO2 to condense into solid form. In our own solar system, the CO2 frost line lies beyond Neptune, where the outermost comets originate from the Kuiper belt and the distant Oort cloud. If 3I Atlas formed in a similar region around another star, it would have been subjected to the same frigid conditions, preserving volatile ices that are now being released as it approaches the sun. The presence of water ice, carbon monoxide, and carbonyl sulfide further reinforces this hypothesis, indicating that 3I Atlas's parent star system may have shared many of the same chemical building blocks as our own. However, the parent star of 3I Atlas remains elusive. Due to the vast distances it has traveled and the long timescale of its journey, the comet has been thoroughly mixed with other interstellar objects, making it nearly impossible to trace back to a specific origin. Unlike 1I Oumuamua and 2I Borisov, which are believed to have been ejected from individual planetary systems, 3I Atlas's trajectory suggests a more complex history of gravitational interactions. AMPER's study by Yang Guo and collaborators in September 2025 revealed that the comet may have passed within 1 parsec, 3.3 light-years, of 25 known stars in the past 10 million years. These close encounters could have altered its trajectory, accelerating or decelerating its motion as it drifted through the galaxy. The cumulative effect of these interactions may have masked its original path, making it difficult to determine whether it was ejected from a single planetary system or formed in a dense stellar nursery where multiple stars contributed to its dynamical history. Despite the uncertainties, the composition of 3I Atlas provides valuable clues about the nature of its parent star. If the comet is a member of the thick disk population of the Milky Way, its parent star was likely a low metallicity object, with a heavy element abundance of at least 40% of the Sun's. This suggests that 3I Atlas formed in an earlier phase of the galaxy's evolution, when stars were less enriched in metals compared to the current stellar population. The thick disk, which contains some of the oldest stars in the Milky Way, is thought to have formed billions of years ago. And if 3I Atlas is indeed a relic of that era, it may carry the chemical fingerprints of an ancient planetary system. The high CO2 abundance in its coma could be a remnant of a different galactic environment, where the distribution of ices and organic molecules varied from what we observe in our own solar system. By studying the isotopic composition of CO2 and other volatiles in 3I Atlas, scientists hope to determine whether its parent star system was chemically distinct from ours, offering a rare glimpse into the diversity of planetary formation in the universe. The ejection of 3I Atlas from its parent star system was likely the result of a gravitational perturbation, a common fate for comets and other small bodies in the outer reaches of planetary systems. In our own solar system, the gravitational influence of giant planets like Jupiter and Saturn has long been known to scatter comets into the Oort cloud, where they remain in stable, distant orbits for millennia. AMPER's similar process could have occurred in 3I Atlas's parent system, where a close encounter with a massive planet or a passing star may have disrupted its orbit, sending it on a trajectory toward the interstellar void. The comet's high hyperbolic excess velocity of 58 kilometers per second indicates that it was ejected with considerable energy, possibly due to a strong gravitational slingshot event. Whether this event occurred in a binary star system, where the gravitational tug-of-war between two stars could have accelerated the comet to its current speed, or in a more conventional planetary system, remains an open question. regardless of the mechanism. 3I Atlas's journey serves as a testament to the chaotic and dynamic nature of planetary formation, where the delicate balance between gravitational forces can determine the fate of entire worlds. The physical characteristics of 3I Atlas reveal a dynamic and evolving celestial body, shaped by the interplay of its internal composition and the external forces of the solar system. At its core, the comet harbors a nucleus composed of a mixture of volatile ices and rocky material, a structure common to comets across the galaxy. However, the precise dimensions of 3I Atlas's nucleus remain uncertain, as it is partially obscured by a dense coma of gas and dust. High-resolution images captured by the Hubble Space Telescope in July 2025 suggest that the nucleus has a diameter ranging between 0.32 and 5.6 kilometers, with the most likely estimate placing it below 1 kilometer. This relatively small size is consistent with the comet's low mass and the limited amount of material it is capable of ejecting into space. The uncertainty in the nucleus's size stems from the difficulty of distinguishing its intrinsic brightness from that of the coma, which is illuminated by the sun's radiation and contributes significantly to the comet's overall luminosity. The coma of 3I Atlas, a cloud of gas and dust that envelops the nucleus, is a direct result of the sun's heating and the sublimation of volatile ices. As the comet approaches the sun, the increasing temperatures cause the ices within the nucleus to transition from solid to gas, a process known as sublimation. This rapid phase change releases trapped gases and dust particles, forming the diffuse and expanding coma that surrounds the nucleus. Observations by the Gran Telescopio Canarias in July 2025 revealed that 3I Atlas's coma spans approximately 26,400 by 24,700 kilometers in diameter, roughly twice the size of Earth. The coma's elongated shape and varying density suggest that the comet's surface is uneven, with regions of higher activity producing stronger outflows of material. The size and structure of the coma evolve as the comet progresses along its trajectory, growing larger and more diffuse as the sun's influence intensifies. By the time 3I Atlas reaches perihelion, the coma is expected to expand significantly, potentially extending hundreds of thousands of kilometers into space. The composition of 3I Atlas's coma is a critical aspect of its study, as it provides insight into the chemical makeup of the comet's nucleus and the processes that drive its activity. Spectroscopic analyses conducted by the James Webb Space Telescope, JWST, and the SPHEREX mission have revealed that the coma is unusually rich in carbon dioxide, CO2, with smaller quantities of water ice, water vapor, carbon monoxide, CO, and carbonyl sulfide, OCS. The high CO2 abundance is particularly noteworthy, as it exceeds the typical ratios observed in solar system comets, suggesting that 3I Atlas may have formed in a different stellar environment where CO2 was more prevalent. The presence of water ice and water vapor confirms that the comet contains frozen reservoirs of this essential molecule, which sublimates as the comet approaches the sun and contributes to the coma's expansion. The detection of CO and OCS further enriches the chemical profile of 3I Atlas, indicating the presence of complex organic molecules that may have played a role in the formation of prebiotic compounds in the early stages of planetary development. The dust component of 3I Atlas's coma is another key factor in understanding its behavior and evolution. The comet's coma contains a mixture of fine and coarse dust particles, each responding differently to solar radiation and the comet's own outgassing activity. Fine dust grains, measuring just a few micrometers in radius, are ejected at high speeds of up to 22 meters per second, propelled by the pressure of outgoing gas and the sun's radiation. These tiny particles form a diffuse and rapidly dispersing component of the coma, contributing to the comet's overall brightness and spectral signature. Coarse dust grains, on the other hand, are larger and heavier, with radii reaching up to 100 micrometers. These particles are ejected at slower speeds, typically around 2 meters per second, and remain closer to the nucleus for longer periods. The combination of fine and coarse dust gives 3I Atlas's coma a layered structure, with the finest particles forming an extended envelope and the coarser material creating a denser, more compact region near the nucleus. The emission of dust from 3I Atlas is not uniform, as it is influenced by the comet's rotation and the distribution of volatile ices on its surface. Observations by the Hubble Space Telescope in July 2025 indicate that the comet is ejecting approximately 6 kilograms of fine dust and 60 kilograms of coarse dust per second, a rate comparable to that of 2I Borisov, but lower than the typical activity of Jupiter family comets. This moderate level of dust production suggests that 3I Atlas's nucleus is relatively stable, with no immediate signs of fragmentation or sudden outbursts. However, as the comet continues its approach to the Sun, the increasing solar heating may lead to a surge in activity, potentially altering the structure and composition of the coma. The study of 3I Atlas's dust emissions provides valuable insights into the mechanical properties of its nucleus, offering clues about the strength and cohesion of its surface materials. In addition to dust and gas, 3I Atlas's coma contains trace amounts of cyanide, CN, and atomic nickel, Ni, vapor, substances that have been detected in other comets, but remain poorly understood in the context of interstellar objects. The emission of CN is a common feature in cometary activity, as it is often produced by the breakdown of organic compounds under the influence of solar radiation. The presence of atomic nickel, however, is less frequently observed and presents a unique challenge for scientists. Unlike iron, which is commonly found in comets and is typically released in tandem with nickel, no iron emission was detected in 3I Atlas, raising questions about the nature of the nickel source. One possibility is that the nickel is released through the decomposition of nickel-containing organic compounds, a process that may be facilitated by space weathering. The absence of iron suggests that 3I Atlas may have a metal-poor composition, distinguishing it from many solar system comets. As research continues, the role of these emissions in shaping the comet's behavior and chemical evolution will become clearer, offering new insights into the diversity of interstellar comets. The physical characteristics of 3I Atlas paint a picture of a dynamic and complex celestial body, shaped by the forces of the solar system and the legacy of its interstellar origins. From its small, icy nucleus to its expansive gas-rich coma, every aspect of the comet reflects the intricate processes that govern the evolution of comets in the universe. As 3I Atlas continues its journey through the inner solar system, each observation brings us closer to unraveling the mysteries of this interstellar traveler, revealing the hidden connections between our world and the vast expanse of the cosmos. The idea of launching a dedicated space mission to intercept 3I Atlas presents a formidable challenge, one that underscores the immense difficulty of exploring interstellar objects. Given the comet's rapid trajectory and the limited time available for planning and execution, any attempt to dispatch a spacecraft from Earth after its discovery on 1 July 2025 would require an unprecedented delta V, the change in velocity necessary to alter a spacecraft's orbit to match the comet's speed. Current propulsion technologies, even the most advanced ion thrusters and chemical rockets, fall short of achieving the required del V of at least 24 kilometers per second. This stark reality renders a direct Earth-launched mission infeasible, with the technology available at the time of 3I Atlas's discovery. However, a theoretical study conducted in July 2025 by Atsuhiro Yaginuma and collaborators proposed an alternative approach, launching a space probe from Mars. Due to the planet's lower escape velocity and its position relative to 3I Atlas's trajectory, a Mars-based mission could achieve the necessary del V of approximately 5 kilometers per second, making an encounter with the comet significantly more viable, while a Mars-launched mission remains speculative. Existing spacecraft in orbit around Mars may have the opportunity to observe 3I Atlas during its close approach to the planet in October 2025. On 3 October 2025, the comet will pass at a distance of 0.19 astronomical units, 28 million kilometers, from Mars, bringing it within range of the red planet's orbiting satellites. Instruments aboard these spacecraft, such as cameras and spectrometers, could capture high-resolution images and detailed compositional data of the comet as it glides past. The Mars Reconnaissance Orbiter, for example, is equipped with the High-Resolution Imaging Science Experiment, HiRISE, a camera capable of resolving features as small as 30 centimeters on the Martian surface. If directed toward 3I Atlas, HiRISE could provide valuable insights into the comet's structure, surface features, and activity patterns. Similarly, the Mars Atmosphere and Volatile Evolution MAVEN mission, designed to study the Martian atmosphere, could analyze the comet's interaction with the solar wind and the composition of its coma. These observations would complement ground-based and space-based telescopic studies, offering a multifaceted perspective on 3I Atlas's behavior as it approaches perihelion. Beyond Mars, other spacecraft positioned in the inner solar system may also contribute to the study of 3I Atlas. The Juno spacecraft, currently in orbit around Jupiter, is unlikely to be reoriented to observe the comet, as it lacks the maneuverability and fuel reserves required for such an operation. Additionally, the Psyche spacecraft, en route to a metal-rich asteroid of the same name, will pass within 0.302 AU 45.2 million kilometers of 3I Atlas on 4 September 2025, while the Jupiter Icy Moons Explorer Betelgeuse will come within 0.4028 AU 64.0 million kilometers on 4 November 2025. Although these distances are considerable, the onboard instruments of these spacecraft could still detect the comet's faint emissions, particularly in the infrared spectrum. The challenge, however, lies in commanding these spacecraft to observe 3I Atlas while balancing their primary missions. Any deviation from their intended objectives introduces risks, including the potential for mission-critical errors. Nonetheless, the prospect of capturing even indirect data from these distant vantage points enhances the scientific value of 3I Atlas's passage through the solar system. As the comet moves beyond Mars and toward its perihelion, the focus shifts to observing its activity as it reaches its closest point to the Sun. During this phase, 3I Atlas will be at its most active, with the Sun's intense radiation sublimating ices from its nucleus and driving the release of gas and dust. Spacecraft operating in the vicinity of the inner solar system, such as those stationed at Lagrange points or conducting heliospheric studies, may have the opportunity to monitor the comet's behavior in real time. The Solar and Heliospheric Observatory, SOHO, for instance, is equipped with coronagraphs that block the Sun's glare, allowing it to detect faint comets passing close to the Sun. If 3I Atlas exhibits a sudden outburst or fragmentation event, SOHO could provide critical data on the comet's structural integrity and the mechanisms that govern its disintegration. Similarly, the Parker Solar Probe, designed to study the Sun's corona, may capture indirect measurements of 3I Atlas's interaction with the solar wind, offering insights into the comet's magnetic and plasma environment. The limitations of current space exploration capabilities highlight the necessity for future missions tailored to the study of interstellar objects. While 3I Atlas's trajectory precludes a direct rendezvous with a spacecraft, its passage through the solar system serves as a catalyst for developing new technologies and strategies for intercepting interstellar visitors. Concepts such as lightweight, high-speed probes powered by advanced propulsion systems, such as nuclear thermal or electric propulsion, are being explored for future missions that could respond rapidly to the detection of interstellar objects. Additionally, the deployment of autonomous AI-driven spacecraft capable of adjusting their trajectories in real time could revolutionize our ability to study these celestial wanderers. As humanity continues to push the boundaries of space exploration, the lessons learned from 3I Atlas will inform the design of future missions, ensuring that we are better prepared to intercept and investigate the next interstellar visitor that graces our cosmic neighborhood. Amidst the scientific scrutiny of 3I Atlas's trajectory, composition, and behavior, an unconventional hypothesis emerged, one that challenged the prevailing consensus and ignited a firestorm of debate within the scientific community. On 16 July 2025, a paper published by astrophysicist Avi Loeb and colleagues from the Initiative for Interstellar Studies proposed that 3I Atlas could be an extraterrestrial spacecraft rather than a natural interstellar comet. Loeb's argument centered on several perceived anomalies: the object's apparent size, its trajectory aligned with the ecliptic plane, and the lack of clear cometary features in early observations. He suggested that these characteristics deviated from what would be expected of a typical comet, and instead aligned with the signatures of an artificial construct. While Loeb acknowledged that the most probable explanation was that 3I Atlas was a natural interstellar object, he emphasized the importance of considering alternative interpretations, arguing that extraordinary claims should not be dismissed outright. The scientific community responded with swift skepticism, with many researchers highlighting the flaws in Loeb's reasoning and the overwhelming evidence supporting 3I Atlas's cometary nature. Astronomer Chris Lintert, for instance, criticized the hypothesis as speculative and lacking empirical foundation, noting that the object had already exhibited definitive signs of cometary activity. Subsequent observations confirmed the presence of carbon dioxide, water vapor, and cyanide in 3I Atlas's coma, chemical signatures unmistakably linked to cometary sublimation. The detection of these volatile compounds, along with the comet's well-documented trajectory, strongly supported the conclusion that 3I Atlas was a natural object rather than an artificial spacecraft. Furthermore, the alignment of its trajectory with the ecliptic plane was not as anomalous as Loeb suggested. It was simply a coincidence, as the comet's path was determined by the gravitational forces acting upon it rather than any intentional design. Darrell Seligman, one of the first researchers to publish a detailed study on 3I Atlas, publicly rejected the alien hypothesis, stating that the evidence for the comet's natural origin was unequivocal. He emphasized that numerous telescopic observations had demonstrated classical cometary features, including the release of gas and dust in response to solar heating. Seligman also pointed out that Loeb's statistical analysis of 3I Atlas's trajectory contained methodological flaws, further undermining the credibility of the hypothesis. Similarly, astrophysicist Scott Manley critiqued Loeb's approach, arguing that the burden of proof for an artificial explanation was extraordinarily high and that the available data did not justify such a claim. The consensus among the broader scientific community was clear. While it was important to maintain an open mind, the alien hypothesis lacked the necessary evidence to warrant serious consideration. The controversy surrounding 3I Atlas underscored the delicate balance between scientific curiosity and rigorous analysis. While Loeb's speculation sparked public interest in the possibility of extraterrestrial technology, it also highlighted the dangers of overinterpreting incomplete data. The scientific process relies on falsifiability and reproducibility, and in the case of 3I Atlas, the overwhelming evidence supported a natural explanation. Nevertheless, the debate served as a valuable reminder that science thrives on questioning assumptions and exploring unconventional ideas, even when they ultimately prove incorrect. As 3I Atlas continues its journey through the solar system, the discussion surrounding its nature will evolve, guided by new observations and the relentless pursuit of truth in the face of cosmic uncertainty. As the comet moves beyond the reach of our telescopes, it leaves behind a trail of unanswered questions. The search for interstellar objects is far from over, and future discoveries may yet challenge our understanding of the universe. For now, 3I Atlas stands as a testament to the complexity of celestial phenomena, reminding us that while science provides the tools to explore the unknown, the cosmos remains a realm of infinite mystery. The study of interstellar comets is just beginning, and with each new visitor, we draw closer to unraveling the secrets of the galaxy, and perhaps one day to finding evidence of life beyond our world. In the vast, silent expanse of the cosmos, where stars burn like distant beacons and planets drift in their ancient orbits, a solitary traveler emerged, a comet unlike any seen before. Discovered on 1 July 2025 by the asteroid Terrestrial Impact Last Alert System, Atlas in Chile, 3I Atlas arrived as a whisper from the depths of interstellar space, a relic of another star's birthright. Its name, etched into the annals of astronomical history, marks it as the third confirmed interstellar object to grace our solar system. Yet 3I Atlas is more than a fleeting visitor. It is a messenger, bearing secrets of distant worlds and the chaotic dance of stellar nurseries. This comet, hurtling through the void at 58 kilometers per second, defies the gravitational pull of the sun, its trajectory, a hyperbolic arc that will carry it back into the galactic abyss. But its passage is not merely a spectacle for telescopes and observatories. 3I Atlas is a bridge between the familiar and the unknown, a fragment of another star system's debris field, born in the crucible of a protoplanetary disk and cast adrift by forces we can scarcely comprehend. As it glides past the orbits of Mars and Venus, its coma glowing faintly with carbon dioxide and water ice, it invites us to ponder the universality of cosmic processes and the shared origins of all matter in the Milky Way. To witness 3I Atlas is to glimpse the raw material of worlds beyond our own. Its journey, though brief in human terms, stretches across eons. If it hails from the Milky Way's thick disk, it may be 7 billion years old, older than Earth itself. In its fragile nucleus, we see the echoes of a star's youth, the frozen remnants of a time when planets were forming and stars were colliding. And as it disappears into the darkness once more, it leaves behind a question as profound as the universe itself. What else lies beyond the edge of our cosmic neighborhood, waiting to be found? When 3I Atlas was first spotted in the constellation Serpens Cauda, its origins were shrouded in mystery. At a distance of 4.5 AU from the Sun, it moved at a blistering speed of 61 kilometers per second, far exceeding the velocities of typical solar system objects. Initial observations by the Atlas survey, combined with follow-ups from the Zwicky Transient Facility and amateur astronomers, quickly revealed its true nature. An interstellar interloper, its hyperbolic trajectory, defined by an eccentricity of 6.141, the highest of any known interstellar object, confirmed that it was not bound to the Sun. Instead, 3I Atlas was on a one-way journey, a traveler from the depths of the galaxy. The discovery of 3I Atlas was a triumph of modern astronomy, made possible by cutting-edge surveys like Atlas and the Vera C. Rubin Observatory. Yet, its story began long before its detection. Tracing its path backward through the cosmos, astronomers determined that it originated from the direction of the Milky Way's galactic center, near the southern celestial hemisphere. Unlike its predecessors 1I Oumuamua and 2I Borisov, which approached from the solar apex, 3I Atlas's southern origin was a surprise. This hinted at a population of interstellar objects that may be more common than previously thought, hidden in the dense starfields of the galactic plane. As 3I Atlas drew closer, its true nature unfolded. The Hubble Space Telescope revealed a coma spanning tens of thousands of kilometers, a cloud of gas and dust ejected from its nucleus by the Sun's heat. The James Webb Space Telescope detected a staggering abundance of carbon dioxide, a clue to its formation far from its parent star, beyond the CO2 frost line. Spectroscopic analysis by the Very Large Telescope uncovered cyanide gas and atomic nickel vapor, elements rarely seen in such quantities. These findings painted a picture of a comet forged in the cold outer reaches of another star system, where volatile ices and organic compounds could coalesce into solid bodies. Yet 3I Atlas's most astonishing trait is its age. If it belongs to the thick disk population of the Milky Way, its nucleus could be 7.6 to 14 billion years old, far older than the solar system. This implies that 3I Atlas predates the formation of the Sun and its planets, a relic from a time when the galaxy was young and turbulent. Its survival across eons is a testament to the resilience of cometary bodies, capable of enduring the harshness of interstellar space. The scientific community raced to study 3I Atlas, deploying every tool at their disposal to decode its mysteries. The Nordic Optical Telescope and the Tidey Observatory confirmed its cometary activity, observing a diffuse coma and a faint tail stretching into the void. By July 2025, the comet's reddish hue, reminiscent of the interstellar comet 2I Borisov, suggested a composition rich in irradiated organic compounds. As it neared the Sun, the Vera C. Rubin Observatory captured its growing coma, while the transiting exoplanet survey satellite TESS revealed that 3I Atlas had been active as early as May 2025, when it was 6.4 AU from the Sun. The James Webb Space Telescope's infrared spectrometer became a key instrument in unraveling the comet's chemistry. JWST's data showed that 3I Atlas's coma contained not only CO2 but also water ice, carbon monoxide, and carbonyl sulfide. The presence of heavy CO2 isotopes hinted at a history of prolonged exposure to cosmic radiation. Meanwhile, the Swift Observatory detected water vapor and hydroxide ions, while the Very Large Telescope identified cyanide and nickel vapor. These elements, though common in solar system comets, were present in proportions that defied expectations, challenging existing models of cometary evolution. Perhaps the most enigmatic aspect of 3I Atlas was its rotation. Early observations suggested a period of approximately 16.79 hours, but the comet's dusty coma complicated measurements. By August, its brightness variations had diminished, indicating that increased activity was obscuring the nucleus. The Hubble's ultraviolet spectroscopy in November 2025 promised further insights, as scientists sought to determine the sulfur-to-oxygen ratio in its gas emissions, a signature of its parent star's composition. Yet not all questions were resolved without controversy. In July 2025, astrophysicist Avi Loeb speculated that 3I Atlas might be an alien spacecraft, citing its trajectory and lack of identifiable chemicals. Though this hypothesis was met with skepticism, it underscored the comet's uniqueness. Subsequent observations by JWST and the Swift Observatory confirmed its cometary nature, detecting CO2, water, and CN gas. The debate, however, highlighted the importance of remaining open to the unknown, even as science clings to empirical evidence. As 3I Atlas departed the inner solar system in late 2025, its legacy lingered in the minds of scientists and stargazers alike. From its discovery by the Atlas survey to its final observations by the James Webb Space Telescope, the comet had illuminated the path of interstellar exploration. Yet 3I Atlas was only the beginning. With the advent of next-generation observatories like the Vera C. Rubin Observatory, humanity stood on the precipice of a new era, one where interstellar objects would no longer be rare curiosities, but routine subjects of study. Future missions, such as the proposed Interstellar probe, aim to intercept such travelers, analyzing their chemistry and structure with unprecedented precision. Mars-based observatories, with their vantage point beyond Earth's atmospheric interference, could serve as staging posts for deep space investigations. The challenges are immense. Escaping the solar system requires delta V far beyond current capabilities, and the vast distances between stars demand patience. Yet the rewards are equally profound. Each interstellar object offers a window into the diversity of planetary systems, their histories, and the universal processes that shape them. As 3I Atlas faded into the cosmic dark, it left behind a question as timeless as the stars themselves. Are we truly alone in the universe? Or is the Milky Way teeming with wanderers like this one, carrying the seeds of life across the void? In its quiet passage, 3I Atlas reminded us that the cosmos is not a silent expanse, but a living, breathing tapestry of motion and mystery. And as we turn our eyes skyward, we do so not just as observers, but as participants in the great cosmic dance, a dance that began long before us and will endure long after. In the vast, uncharted expanse of the cosmos, where the boundaries between stars blur into endless darkness, 3I Atlas emerged, a wanderer from the depths of interstellar space. Discovered on 1 July 2025 by the Asteroid Terrestrial Impact Last Alert System, Atlas Station in Chile, this enigmatic comet entered the inner solar system at a staggering distance of 4.5 astronomical units (AU) from the Sun, hurtling through the void at a velocity of 58 kilometers per second. Unlike the familiar celestial bodies of our solar system, 3I Atlas does not belong to the gravitational embrace of the Sun. Instead, it follows a hyperbolic trajectory, a cosmic arrow aimed outward, destined to vanish into the interstellar abyss once more, as the third interstellar object confirmed to traverse our celestial neighborhood, following the mysterious 1I Oumuamua and the more recent 2I Borisov. 3I Atlas carries with it the secrets of distant star systems, remnants of ancient stellar nurseries, and the echoes of a universe far older and vaster than our own. Its arrival is not merely a scientific event, but a profound reminder of our interconnectedness with the cosmos. a bridge spanning the chasm between the familiar and the infinite. The story of Three-Eye Atlas is one of cosmic kinship. It is a traveler from a realm beyond our solar system, a relic of a stellar system long ago disrupted, cast adrift on a journey that defies the gentle gravitational rhythms of home. Its nucleus, cloaked in a coma of gas and dust, glows faintly against the backdrop of the Milky Way, a spectral reminder of the chaotic birth of worlds. Every particle it sheds, every molecule it emits, whispers of the conditions in its distant origin, a place where stars burn differently, where planetary systems form under alien skies. As Three-Eye Atlas approaches its closest point to the Sun on 29 October 2025, it offers a fleeting opportunity to glimpse the chemistry of another world, to trace the fingerprints of a stellar family tree we have never seen. In its brief passage, it challenges us to reconsider the boundaries of our understanding, to recognize that the universe is not a collection of isolated systems, but a tapestry woven from countless threads of shared history. Yet, Three-Eye Atlas is more than a scientific curiosity. It is a symbol of the universe's boundless mystery, a celestial nomad that stirs the imagination and invites us to ponder our place in the grand cosmic narrative. Its journey through the solar system is a mirror of our own existence, born from the remnants of a dying star, shaped by forces beyond our control, and driven by an innate desire to explore the unknown. As we track its path across the heavens, we are reminded that we too are travelers in a universe teeming with stories yet to be told. The arrival of Three-Eye Atlas is not just an event in the night sky, it is a call to wonder, a reminder that the cosmos is alive with the possibility of discovery. At its core, Three-Eye Atlas is a comet, a celestial body forged in the cold, dark reaches of interstellar space. Like its solar system counterparts, it consists of a solid nucleus composed of ice, rock, and organic compounds, surrounded by a glowing coma, a cloud of gas and dust, expelled by the sun's radiant energy. Yet the specifics of Three-Eye Atlas's composition reveal a tale unlike any other. Observations by the Hubble Space Telescope suggest that its nucleus, though shrouded in a veil of dust, is likely no more than a kilometer in diameter. This diminutive size belies its immense influence, as the nucleus serves as the source of the comet's activity. As Three-Eye Atlas draws closer to the Sun, the heat sublimates its volatile ices, transforming them from solid to gas in an instant. This process releases torrents of carbon dioxide, water vapor, carbon monoxide, and even traces of cyanide and atomic nickel, forming the coma and the faint, elongated tail that stretches behind the nucleus. The James Webb Space Telescope's infrared gaze has unveiled a particularly striking feature. The coma is unusually rich in carbon dioxide, a gas far more abundant than typically seen in solar system comets. This anomaly hints at a formation environment where temperatures were frigid enough for CO2 to freeze into ice, perhaps in the outermost reaches of a distant protoplanetary disk. The coma of Three-Eye Atlas is not merely a passive cloud. It is a dynamic, evolving entity. High-resolution images captured by the Gran Telescopio Canarias reveal its elliptical shape, spanning tens of thousands of kilometers, twice the diameter of Earth. The dust within it ranges in size from microscopic grains to larger particles, each propelled by the force of solar radiation pressure. Smaller grains are swept away, forming the comet's anti-solar tail, while heavier particles linger closer to the nucleus, creating a denser, more opaque region. This interplay of forces gives rise to the comet's distinctive appearance, a glowing halo of activity that shifts and changes as Three-Eye Atlas progresses through its solar encounter. The reddish hue of the coma, observed across multiple wavelengths, is attributed to the presence of irradiated organic compounds, complex molecules forged by the relentless bombardment of cosmic rays and solar wind. These same compounds, found in the tails of solar system comets and the surfaces of D-type asteroids, serve as a cosmic signature, linking Three-Eye Atlas to the broader tapestry of interstellar matter. Perhaps the most intriguing aspect of Three-Eye Atlas is its chemical diversity. Spectroscopic analysis conducted by the Very Large Telescope and the Swift Observatory have identified the presence of cyanide gas and atomic nickel vapor, substances rarely detected in cometary environments. The emission of nickel in particular raises questions about the comet's internal structure and the processes that govern its outgassing. While nickel is a common component of planetary cores, its presence in a comet suggests a unique history, one where the nucleus may have been subjected to extreme conditions, such as the shockwaves of a nearby supernova or the gravitational turmoil of a collapsing star system. The absence of detectable iron vapor further complicates the picture, hinting at a compositional asymmetry that remains poorly understood. These findings underscore the importance of 3I Atlas as a laboratory for studying the chemistry of the interstellar medium, a window into the raw materials that give rise to planets and life. Despite the wealth of data gathered by Earth-based and space-based observatories, the true nature of 3I Atlas's nucleus remains elusive. The uncertainty stems from the difficulty of disentangling the light reflected by the nucleus from the glow of the coma. Early estimates place the nucleus's diameter as high as 10 kilometers, but subsequent observations have narrowed the range to between 0.32 and 5.6 kilometers, with the most probable value falling below 1 kilometer. This ambiguity highlights the challenges of observing interstellar objects, which are often faint, fast-moving, and embedded in the glare of their own activity. Yet, even with these limitations, the data collected from 3I Atlas has already reshaped our understanding of cometary evolution. Its high rate of dust ejection, comparable to that of 2I Borisov, suggests a nucleus with a fragile, porous structure, vulnerable to the stresses of solar heating. This fragility raises the possibility of fragmentation events, where the comet's nucleus could break apart under the strain of its own activity, releasing a final burst of gas and dust before vanishing from view. The Sun's influence on 3I Atlas is both a catalyst and a constraint. At a distance of 1.36 AU from the Sun at perihelion, the comet resides in a transitional zone between the inner and outer solar system, where temperatures are warm enough to drive sublimation, but not so intense as to destroy its delicate structure entirely. This balance allows 3I Atlas to exhibit a steady, prolonged outgassing, rather than the explosive burst characteristic of closer passing comets. The TESS satellite's observations, which captured the comet's activity as early as May 2025, further demonstrate that even at distances exceeding 6 AU, the comet's volatile ices, primarily CO2 and CO, are sufficient to sustain its activity. This resilience speaks to the uniqueness of 3I Atlas, a body that has retained its primordial composition despite eons of isolation in the interstellar void. The origins of 3I Atlas lie in the depths of the Milky Way, a region where the interplay of stars and dark matter has sculpted the galaxy's structure over billions of years. By analyzing the comet's hyperbolic trajectory and its velocity components, astronomers have deduced that it hails from either the thin or thick disk of the Milky Way. The thick disk, a population of older stars with lower metallicities, suggests that 3I Atlas could be at least 7 billion years old, far older than the solar system itself. This staggering age places the comet among the most ancient objects in the universe, a relic from an era when the galaxy was still in its infancy. If 3I Atlas indeed originates from the thick disk, its journey through interstellar space would have spanned epochs of galactic evolution, during which it may have traversed the spiral arms of the Milky Way, skirted the galactic center, and encountered the gravitational tugs of countless stars. Each of these interactions would have subtly altered its trajectory, nudging it closer to the solar system until the day it was discovered in the dense star fields of Sagittarius. The comet's trajectory is a testament to the chaotic dance of gravity in the cosmos. With an orbital eccentricity of 6.141, the highest recorded for an interstellar object, 3I Atlas's path is nearly straight, a stark contrast to the curved orbits of solar system bodies. This trajectory is not random. It is the product of a velocity vector that exceeds the Sun's escape speed by a margin of 58 kilometers per second. Such a velocity implies that 3I Atlas was not ejected from a planetary system through a single violent event, but rather accelerated to its current speed by a combination of gravitational interactions. Theories abound regarding its parent star system. Perhaps it was flung from a binary system by the gravitational pull of a companion star, or maybe it was scattered by the migration of giant planets in a distant solar system. What is certain is that 3i Atlas's journey has been long and lonely, a voyage spanning thousands of parsecs before its arrival in the solar system. The comet's alignment with the ecliptic plane adds another layer of intrigue to its story. Unlike 1i Oumuamua, which approached the solar system from above the ecliptic, and 2i Borisov, which came from below, 3i Atlas's trajectory is retrograde and inclined by a mere 5 degrees relative to the plane of the planets. This alignment suggests a possible connection to the galactic disk, where the majority of stars reside. The fact that 3i Atlas originated from the southern celestial hemisphere, opposite the solar apex, the direction of the sun's motion through the galaxy, is particularly surprising. Previous models predicted that interstellar objects would predominantly come from the solar apex, where the sun's velocity through the local interstellar medium would increase the likelihood of encounters. The discovery of 3i Atlas challenges these assumptions, hinting that southern origin interstellar objects may be more common than previously thought, or that our observational biases have obscured their true distribution. Either way, 3i Atlas's trajectory underscores the complexity of the galaxy's dynamics, a reminder that the universe is a vast interconnected web of motion and interaction. The potential for 3i Atlas to interact with planets in the solar system has been carefully studied, though its path ensures that it will remain a distant spectator. The comet will pass within 0.19 AU of Mars on 3 October 2025, a proximity that may allow Martian orbiters to capture close-up observations. Similarly, its 0.36 AU encounter with Jupiter in March 2026 will test the limits of the gas giant's gravitational influence, though it is unlikely to alter 3i Atlas's trajectory significantly. These close approaches highlight the comet's role as a transient visitor, a guest in the solar system that will depart without leaving a permanent mark. Yet, its interactions with these planets offer a unique opportunity to study the effects of planetary gravity on interstellar objects, providing insights into the mechanisms that govern the ejection of comets from their native systems. The feasibility of sending a spacecraft to intercept 3i Atlas has been a topic of discussion among planetary scientists. Given its high velocity and the limited time available after its discovery, a mission launched from Earth would require a delta V of at least 24 kilometers per second, an impossibility with current propulsion technology. However, a launch from Mars, where the comet's trajectory brings it closer to the red planet, presents a more viable option. AMPER's probe, departing from Mars in late 2025, could achieve the necessary velocity with a delta V of approximately 5 kilometers per second, allowing it to conduct a flyby as 3i Atlas passes within 0.19 AU of Mars. Such a mission would revolutionize our understanding of interstellar comets, offering direct measurements of the comet's composition, structure, and activity. While logistical challenges and budgetary constraints may delay such an endeavor, the prospect of a dedicated mission to 3i Atlas underscores the growing interest in interstellar objects as targets for exploration. Beyond the realm of science, 3i Atlas has sparked a philosophical debate about the nature of cosmic visitors. In July 2025, astrophysicist Avi Loeb and colleagues speculated that the comet could be an extraterrestrial spacecraft, citing its anomalous trajectory and the lack of detectable organic molecules as potential signs of artificial origin. While this hypothesis has been met with skepticism by the broader scientific community, it reflects a broader curiosity about the possibility of life beyond Earth. Subsequent observations by the James Webb Space Telescope and the Very Large Telescope have confirmed the presence of carbon dioxide, water vapor, and cyanide in 3i Atlas's coma, aligning it with the characteristics of natural comets. Nonetheless, the debate serves as a reminder that the universe is full of surprises and that our understanding of interstellar objects is still in its infancy. As 3i Atlas continues its journey beyond the solar system, its legacy is already being etched into the annals of human knowledge. The data it has provided, its composition, trajectory, and activity, has deepened our understanding of interstellar objects and their role in the galactic ecosystem. Yet perhaps the greatest impact of 3i Atlas lies in the questions it has inspired. How many other interstellar comets and asteroids drift silently through the cosmos, unseen? What secrets do their chemical signatures hold about the formation of stars and planets in distant systems? And what might they reveal about the universality of life's building blocks? These questions, unanswered for now, propel us forward in our quest to decode the universe. The story of 3I Atlas is not one of isolation but of connection. It reminds us that the cosmos is a vast interconnected web, where the fates of stars, planets, and comets are intertwined across eons of time. Its arrival in the solar system is a fleeting moment in the grand scale of the universe, yet it carries with it the weight of history, a history that transcends the boundaries of individual star systems. In tracing 3I Atlas's path, we are not merely observing a comet. We are participating in the unfolding narrative of the Milky Way, a participant in a story that is as old as the galaxy itself. As the comet fades from view, its influence lingers. The data it has left behind will guide future generations of scientists who will build upon our discoveries to explore the mysteries of the cosmos. The instruments we have used to study 3I Atlas, Hubble, James Webb, and the ground-based telescopes that tracked its passage will continue to refine our ability to detect and analyze interstellar visitors. And as we look to the future, we know that 3I Atlas is not the last of its kind. More interstellar objects will come, each carrying its own unique story, each offering a glimpse into the vast uncharted realms of the universe. In the end, 3I Atlas is more than a comet, it is a beacon, illuminating the path forward as we strive to understand our place in the cosmos.